Look up at the night sky on a clear, dark evening, and you'll see a scattering of stars, a familiar cosmic tapestry. But if you could peer just a little deeper, beyond what the naked eye can see, you would find a universe teeming with islands of stars so vast and so strange they defy comprehension. One of those islands, a swirling vortex of light some 28 million light-years away, holds secrets that have captivated and confounded astronomers for generations. It's known as the Sombrero Galaxy, and from our vantage point, it looks exactly like its namesake, a wide-brimmed cosmic hat floating in the absolute silence of space. What could possibly be hidden within that stunning silhouette? What mysteries lie along its dark, defining dust lane or within its brilliant, overstuffed core? Tonight, we are going on a journey to find out, venturing directly into the heart of this celestial marvel to uncover 50 of its most bizarre and enigmatic objects, each one a puzzle that challenges our very understanding of how galaxies live and die. This isn't just a tour of pretty pictures, it's a deep dive into the unknown, a voyage to the edge of scientific understanding where every discovery raises even more profound questions. The Sombrero Galaxy, or Messier 104, is more than just a beautiful face. It is a cosmic laboratory, a place where the normal rules of physics seem to be stretched and tested. Its most striking feature is that razor-sharp dark lane of dust, a stark divide that cuts across a core of incandescent starlight so dense it resembles a glowing jewel. For a long time, we saw it as a single, unified object, a simple side-on spiral. But as our telescopes grew more powerful, we began to see the details, the faint whispers of ancient star clusters, the subtle glow of nebulous clouds, and the telltale signs of gravitational turmoil. Each new observation peeled back a layer, revealing a galaxy of immense complexity and contradiction. It is a place of both serene beauty and violent history, where calm, orderly rotation coexists with the aftermath of catastrophic collisions. The 50 strange objects we'll explore are the key to unlocking that history. They are the survivors, the outliers, the celestial phenomena that simply shouldn't exist according to our standard models. We will encounter star clusters that are far too young for their surroundings, clouds of gas behaving in impossible ways, and gravitational anomalies that hint at the presence of something massive and unseen. Each object is a clue in a grand cosmic detective story, a story that we are only just beginning to piece together, so prepare to have your perspective shifted. We are about to look past the sombrero's beautiful facade and into its strange, beating heart, where the ordinary becomes extraordinary and every answer leads to a new, more thrilling question. To truly appreciate the strangeness of the sombrero, we must begin our journey at its very heart, a place of unimaginable density and power. The first of our 50 strange objects isn't something you can see with light, but rather, its overwhelming gravitational presence that betrays its existence. Lurking at the galactic center is a supermassive black hole, a cosmic monster of staggering proportions. Current estimates place its mass at over 1 billion times that of our own sun. To put that into a perspective that's almost impossible to grasp, that is more than 200 times heavier than the black hole at the center of our own Milky Way. This isn't just a heavy object, it is a gravitational titan whose influence dictates the motion of millions of stars swirling around it. The sheer scale of this entity is our first clue that the Sombrero Galaxy operates on a different set of rules. But the true anomaly, the characteristic that earns it a spot on this list of strangeness, isn't just its immense size but its baffling behavior. According to our current understanding, black holes of this magnitude, often referred to as active galactic nuclei, should be voracious consumers of gas and dust. As this material spirals inward, it heats up to incredible temperatures, creating a brilliant, swirling accretion disk and often shooting out colossal jets of high-energy particles at nearly the speed of light. Yet the Sombrero's black hole is strangely quiet. It possesses the engine of a cosmic quasar, but it's running at a whisper. Observations in X-ray and radio wavelengths reveal only faint, sputtering jet activity, a mere hint of the tremendous power that should, by all rights, be erupting from its core. This paradox is what captivates astronomers. Why is this billion-solar mass giant so lethargic? One compelling theory suggests that the galaxy may have recently undergone a merger, a violent collision with a smaller galaxy that funneled a vast amount of material toward the black hole, creating a brief, spectacular outburst of activity. Now, in the aftermath, the black hole has consumed most of the readily available fuel and has entered a period of relative quiescence. We might be seeing it in a state of cosmic hibernation, a sleeping giant whose past fury is now just a faint echo. Another, even more intriguing possibility is that the very structure of the Sombrero Galaxy is preventing the black hole from feeding. That iconic, razor-sharp dust lane that gives the galaxy its hat-like appearance is a massive ring of cold gas and dust circling the core. This ring may be acting as a regulatory barrier, stifling the flow of material inward and effectively starving the black hole, keeping its immense power in check. This delicate balance between the black hole's gravitational pull and the stability of the surrounding disk creates a strange and precarious cosmic equilibrium. The gravitational warping caused by this colossal mass is profound. It doesn't just pull on stars, it twists the fabric of space-time itself, creating a gravitational well so deep that it accelerates nearby stars to dizzying speeds. Astronomers can measure these velocities, and the stars close to the core are moving so fast that their motion can only be explained by the presence of an incredibly concentrated mass, a mass that can be nothing other than a supermassive black hole. This object is strange because it defies our expectations of how such a massive engine should behave, presenting a quiet, almost serene facade that masks a latent power capable of reshaping its entire galactic home. It is a puzzle of cosmic proportions, a silent king on a stable throne, and our first fundamental piece of evidence that the Sombrero Galaxy is anything but ordinary. But the gravitational enigma at the galaxy's core only deepens when we look even closer, revealing a structural peculiarity that has sparked fierce debate for decades. Our second strange object is the baffling suggestion of a twin nucleus. Most large galaxies, including our own, possess a single, well-defined central hub, a dense concentration of stars marking the gravitational center. Yet, high-resolution observations of the Sombrero, particularly from the Hubble Space Telescope, have repeatedly hinted at something far more complex. The very heart of the galaxy appears to be split, presenting what looks like two distinct brightness peaks nestled side by side within the brilliant core. This isn't just a trick of the light or a blurring effect from our atmosphere. It's a persistent anomaly that refuses to be easily explained, pointing to a dynamic and potentially violent history at the galaxy's center. The existence of a double nucleus would be a monumental discovery, forcing us to rethink the relatively peaceful formation story we often assign to such elegant galaxies. So, what could possibly create this illusion, or perhaps this reality? Astronomers have two primary theories, each more fascinating than the last. The first, and perhaps the most dramatic, scenario involves a second act of cosmic cannibalism. Galaxies grow by consuming smaller neighbors, and if the Sombrero recently devoured a smaller galaxy, that victim's central black hole would not have simply vanished. Instead, it would have been pulled into a long, slow orbital dance around the primary supermassive black hole. This smaller black hole, still possessing the mass of millions of suns, would continue to hold onto its own retinue of stars, creating a second, fainter point of concentrated light and gravity that we perceive as a twin nucleus. The two black holes would eventually merge in a cataclysmic event rippling spacetime with gravitational waves, but for now, they could be locked in a millennia-long orbital embrace, a silent testament to a past galactic collision. The second theory offers a slightly less violent but equally strange explanation. It's possible we're not seeing two objects at all, but rather a single, massively dense disk of stars orbiting the primary black hole at tremendous speeds. If this disk is seen almost perfectly edge-on from our perspective, its shape would be elongated. The ends of this elongation, where more stars are packed along our line of sight, could appear brighter than the center, creating the illusion of two separate bright spots. Imagine a gigantic, glowing pinwheel spinning so fast that its outer edges blur into two distinct clumps of light. We will be witnessing a stellar structure pushed to its physical limits by the overwhelming gravity of the central black hole. This phenomenon, known as a Keplerian disk, would itself be a rare and extreme environment. Confirming either theory is incredibly difficult because the suspected nuclei are so close together and drowned in the intense glare of the surrounding core. It requires pushing our most advanced telescopes to their absolute limits, using sophisticated computer models to subtract the blinding starlight and peer into the heart of the glow. If a twin nucleus is confirmed, the implications for galaxy formation would be profound. It would be the strongest evidence yet that the Sombrero is the product of a recent merger, a cosmic hybrid. This would help explain other oddities, like the strange distribution of its globular clusters and the unusual motion of its stars. The serene beauty of the Sombrero's silhouette would then be a cosmic mask, hiding a turbulent history of collision and consumption that is still playing out in its core. This mystery reminds us that in astronomy, what appears simple and symmetrical often conceals a deeply complex and dynamic reality. Moving outward from the mysterious core, our attention is drawn to the very feature that defines the Sombrero's iconic appearance, that dramatic, pitch-black band of dust encircling its brilliant bulge. For centuries, this dark lane was seen as a textbook example of a simple, flat ring, a serene and orderly structure, but our third strange object reveals this placid image to be an illusion. Advanced observations, particularly in infrared light which can penetrate the dust, have uncovered a startling truth. This is not a flat, stable disk like a vinyl record. It is warped, twisted, and contorted in ways that challenge our understanding of galactic stability. Instead of a neat plane, the dust ring exhibits a distinct S-shaped warp, a characteristic that suggests the entire structure is wobbling or precessing over immense timescales. This kind of distortion doesn't just happen in an isolated, undisturbed galaxy. A stable disk of stars, gas, and dust should, according to basic physics, settle into a flat, rotational equilibrium. The presence of such a pronounced warp is a glaring signpost pointing to a significant gravitational disturbance in the galaxy's recent past, cosmically speaking. It's as if we're looking at a pond long after a stone has been thrown in. The surface is still rippling, telling the story of an impactful event. The most compelling explanation for this cosmic wobble is a past gravitational encounter. One leading theory proposes that the Sombrero Galaxy had a close flyby with a smaller dwarf galaxy millions of years ago. Although this companion may have since been torn apart and absorbed, its gravitational tug as it passed would have been enough to set the massive dust ring oscillating, like a gentle pull on a spinning gyroscope. The disk, composed of billions of tons of gas and dust, doesn't snap back instantly. It continues to wobble, its warp a fossil record of that ancient interaction. Another, even more dramatic, possibility is that the warp is a lingering effect of the same merger event that may have created the potential twin nucleus. If a larger galaxy was consumed, the influx of new material and the resulting gravitational chaos could have torqued the entire disk out of its original plane. This warping has profound consequences for the galaxy's ongoing evolution. A distorted dust lane alters the internal dynamics of the entire system. It can funnel gas flows in unexpected directions, potentially triggering sporadic bursts of star formation in peculiar locations, far from the calm, orderly spiral arms we see in other galaxies. Furthermore, this warp may be directly connected to the strange quietness of the central supermassive black hole. The twisted geometry could be disrupting the smooth flow of gas inward toward the core, effectively starving the black hole and explaining its unusually quiescent state. This single feature, then, is not just a beautiful dark ribbon. It is a dynamic and active structure, a key that links the galaxy's violent past to its present-day mysteries. The serene hat we see from a distance is, upon closer inspection, slightly askew, a permanent tilt that whispers tales of cosmic violence and gravitational drama. While the warped dust lane reveals a history of gravitational disturbance, the true scale of the forces shaping the Sombrero only becomes apparent when we look beyond its visible stars to the very edges of its gravitational influence. The fourth strange object on our list is perhaps the most fundamental, and yet it is one we can never see directly. It is the galaxy's immense, invisible dark matter halo. This isn't a structure made of stars or gas. It's a sprawling, spherical cloud of mysterious particles that envelops the entire luminous galaxy, extending far out into the emptiness of intergalactic space. We know it exists not because we can photograph it, but because of the inexplicable behavior of the stars we can see, especially those tracing the galaxy's outer fringes. According to the established laws of gravity, stars orbiting at the edge of a galaxy should move much more slowly than those near the bright, massive center. Think of our own solar system. Pluto, far from the Sun, orbits at a snail's pace compared to Mercury. But when astronomers measure the orbital velocities of stars in the Sombrero's outer disk, they find something astonishing. These distant stars are hurtling around the galactic center at speeds that are far too high. They are moving so swiftly that the combined gravitational pull from all the visible matter, every single star, every gas cloud, the entire central bulge, is utterly insufficient to hold them in orbit. At such velocities, these outer stars should have long ago flown off into the void, yet they remain bound to the galaxy. The only possible explanation is that they are being whipped around by the gravitational grip of something else, something that adds immense mass but emits no light. That something is dark matter. This invisible halo acts as a cosmic anchor, its gravity providing the extra pull needed to keep the galaxy from flying apart. For the Sombrero, this anchor is strangely, almost unnervingly heavy. Estimates suggest that this dark matter halo contains up to 10 times more mass than all the galaxy's visible components combined. This ratio is unusually high for what appears to be a large, disk-dominated galaxy. In similar spiral galaxies, we often find a more balanced distribution between visible and dark matter. The Sombrero's excessive dark matter content presents a significant puzzle. Why is there so much of it? One compelling idea links back to the galaxy's possible hybrid nature. If the Sombrero is the product of a major merger between two large galaxies, the chaotic collision could have stripped away a significant portion of their visible gas and stars, flinging them out into space. The dark matter, however, being immune to electromagnetic forces and interacting only through gravity, would have remained largely in place, settling into a new, more massive halo around the combined galactic core. What we see today could be a galaxy that has lost a great deal of its luminous mass, leaving behind a dark matter signature that is disproportionately dominant. Another fascinating possibility is that the Sombrero is not a pure spiral galaxy at all, but rather a transitional form on its way to becoming an elliptical galaxy. Giant elliptical galaxies are known to be overwhelmingly dominated by dark matter. The Sombrero's peculiar structure, its massive bulge combined with a thin, disrupted disk, might represent a snapshot of this cosmic evolution where the dark matter halo has already taken precedence, dictating the future fate of the entire system. This invisible structure is arguably the most important object in the entire galaxy. It is the hidden framework upon which the visible sombrero is built, its gravitational field dictating the rotation curve and ensuring the galaxy's long-term stability. It may also be responsible for the warped disk itself, as the gravitational tides from such a massive, asymmetric halo could easily torque the visible matter into its current distorted shape. So, while we celebrate the sombrero for its stunning visual beauty, we must remember that its true form, its immense gravitational bulk, remains shrouded in darkness, a silent testament to the fact that most of the universe is made of something we cannot see and do not yet understand. Yet the gravitational evidence for a violent past extends far beyond the warped disk and into the vast, dark halo itself, manifesting in a spectacular way when we peer at the galaxy's outermost reaches. Our fifth strange object isn't a single entity but a vast and glittering swarm, a population of globular clusters so immense it defies all expectations. Encircling the Sombrero Galaxy like a cloud of ancient fireflies are nearly 2,000 of these dense, spherical collections of stars. To understand why this number is so profoundly strange, consider our own cosmic neighborhood. The Milky Way, a large and respectable spiral galaxy in its own right, is home to about 150 known globular clusters. The Sombrero possesses well over 10 times that number. This isn't just a slight difference, it's a staggering anomaly that immediately sets the Sombrero apart as a galactic heavyweight with a history far more complex than its serene appearance suggests. These clusters are not young. Each one is a fossil relic containing hundreds of thousands of stars bound together by gravity, all born in a single, frantic burst billions of years ago. They represent the oldest stellar populations in a galaxy, and their sheer abundance around the Sombrero points to a history of relentless accumulation. So, where did all these clusters come from? A galaxy doesn't simply form with thousands of these objects, it collects them. The most compelling explanation is a long and dramatic history of cosmic cannibalism. The Sombrero Galaxy, it seems, is a galactic gourmand, and many of these globular clusters are the orphans of its past meals. When a large galaxy like the Sombrero gravitationally pulls in and tears apart a smaller dwarf galaxy, it doesn't just digest the victim stars into its general population. The dwarf galaxy's own globular clusters, being incredibly dense and tightly bound, are remarkably resilient. They can survive the violent tidal forces of the merger intact. As the dwarf galaxy is shredded, its orphan clusters are cast adrift, only to be captured by the immense gravity of the larger galaxy, becoming permanent additions to its swirling entourage. Each of these captured clusters is a strange and silent witness, a celestial tombstone marking a long-dead galaxy. Their orbits, chemical compositions, and even their ages can tell a forensic story. Astronomers can analyze the light from these clusters and find that many have distinct metallic signatures, different ratios of elements like iron and oxygen, that don't match the clusters native to the Sombrero's main body. This is the smoking gun, proving they formed in a different environment far away before being forcibly adopted by their massive new home. This orphan swarm does more than just testify to a violent past. It actively shapes our understanding of what the Sombrero Galaxy truly is. The number and distribution of these clusters are key indicators used to classify galaxies. Giant elliptical galaxies, which are thought to form through the merger of multiple spirals, are renowned for their enormous families of globular clusters, often numbering in the thousands. The Sombrero, with its prominent disk but also its massive bulge and this immense globular cluster system, fits awkwardly into our standard classification boxes. It exhibits characteristics of both a spiral and an elliptical galaxy, making it a probable hybrid or a lenticular galaxy caught in a transitional phase. Its stunning spiral structure might be a temporary feature, a remnant of a disked galaxy that merged with another. its spiral arms not yet fully erased by the gravitational turmoil. The presence of nearly 2,000 globular clusters strongly supports this hybrid identity. It suggests the Sombrero has already undergone at least one, and likely several, significant mergers, each event contributing its own population of orphan clusters to the growing swarm. This makes every single one of those 2,000 points of light more than just a beautiful feature. Each is a clue in a billion-year-old detective story, a piece of evidence pointing to the dynamic, chaotic, and building block nature of galaxy evolution. The serene hat we admire is in reality a trophy case displaying the spoils of its cosmic conquests. But the story of cosmic consumption doesn't end with ancient star clusters. It continues in the form of strange, high-speed rivers of gas flowing through the galactic halo. Our sixth and seventh strange objects are these high-velocity gas clouds, immense structures of primarily hydrogen detected not by their light, but by the radio waves they emit. These are not calm, settled features. They are dynamic and frenetic, with some clouds hurtling toward the galaxy at breakneck speeds while others are being violently ejected out into intergalactic space. This creates a bizarre and contradictory picture of the Sombrero as both a gluttonous consumer and a wasteful expeller of primordial material, all at the same time. The clouds falling inward are like cosmic rainfall, a potential source of fresh fuel for future generations of stars. Their trajectories suggest they are on a long, arching path that will eventually plunge them into the galaxy's disk, potentially triggering new waves of star formation millions of years from now. But what is the source of this incoming gas? One leading theory points back to the galaxy's cannibalistic tendencies. These infalling clouds could be the final, dissipating remnants of a dwarf galaxy that was torn apart by the Sombrero's gravity eons ago. The stars from that dwarf would have been quickly absorbed, but its diffuse gaseous envelope, being less bound by gravity, would have been stretched into long, streaming filaments that are only now completing their fatal descent. They are the last ghosts of a departed galaxy returning to the scene of the crime. Alternatively, this gas might not be a relic of a past merger but a sign of ongoing activity. It could be pristine hydrogen drawn in from the vast, invisible reservoirs of the intergalactic medium, the Sombrero actively feeding from the thin cosmic soup that fills the voids between galaxies. Meanwhile, the clouds shooting outward present an even greater puzzle. Their high velocities, far exceeding the galaxy's escape velocity, mean they are lost to the Sombrero forever. Such powerful outflows are typically associated with intense energy sources, and all evidence points back to the galaxy's enigmatic core. The primary suspect is the combined effect of furious stellar activity near the galactic center. The central bulge of the Sombrero is packed with stars, including many massive, hot, short-lived giants. These stars produce incredibly powerful stellar winds, a constant stream of charged particles blasting off their surfaces. When you concentrate thousands of these stellar powerhouses in a relatively small volume, their collective winds can combine into a colossal gale, powerful enough to push vast quantities of gas right out of the galaxy's gravitational grip. An even more dramatic explanation involves the supermassive black hole itself. Even in its current quiet state, it may experience sporadic, minor feeding events. As small amounts of gas spiral inward, they could be superheated and channeled by magnetic fields into narrow, high-speed jets. While we don't see the massive jets of an active galaxy, these smaller, more frequent outbursts could be enough to act like a cosmic pressure washer, blowing bubbles of gas out into the halo. This constant cycle of infall and outflow is crucial to a galaxy's life story. The incoming gas provides the raw material for new stars, while the outflowing gas regulates that growth, preventing the galaxy from converting all its fuel too quickly. It also enriches intergalactic space with heavier elements forged in stellar interiors, seeding the universe for future generations of galaxies. In the Sombrero, this cycle appears to be operating on an exaggerated scale, another sign of its unique and turbulent nature. These high-velocity clouds are the galaxy's breath, the visible evidence of its dynamic interaction with the cosmos around it, proving that even a seemingly static and beautiful island of stars is a place of constant, violent change. As we move from the grand, sweeping structures of the halo to the intricate details within the galaxy's disk, we encounter a different kind of mystery, one that shines not in visible light, but in some of the highest energy radiation the universe can produce. Our 8th, 9th, and 10th strange objects are a trio of cosmic powerhouses known as ultra-luminous X-ray sources, or ULXs for short. Scattered across the Sombrero, these are not the faint, twinkling points of light we associate with stars. They are pinpoint locations on the X-ray sky that blaze with an intensity that defies simple explanation. To understand their strangeness, we need a scale of cosmic power. At one end, you have stellar mass black holes, the remnants of giant stars. When these black holes pull gas from a companion star, the infalling material heats up and glows in X-rays, creating what we call an X-ray binary. At the other extreme, you have the supermassive black holes at the centers of active galaxies, which can outshine entire galaxies in X-rays. ULXs sit squarely in the middle, producing far more X-ray light than any typical stellar black hole could possibly generate, yet they are not located at the galactic center and are nowhere near as powerful as a true active nucleus. This places them in a bizarre and poorly understood category, and the fact that the Sombrero Galaxy hosts several of them makes it a key laboratory for solving this cosmic puzzle. So, what could these objects possibly be? If a standard stellar black hole simply ate more gas, it wouldn't solve the problem. There's a fundamental limit known as the Eddington limit, which is the maximum brightness an object can achieve based on its mass. Beyond this point, the intense radiation pressure from the infalling material would actually push away any further gas, effectively turning off the faucet. For a ULX to shine so brightly, it must either be breaking this fundamental law of physics, or it must be an object with far more mass than a single star. This is where the leading hypotheses come into play. The first and perhaps most exciting idea is that ULXs are the long-sought intermediate mass black holes. These would be black holes with masses ranging from a few hundred to a few 100,000 times that of our Sun, filling the evolutionary gap between stellar mass black holes and the supermassive giants at galactic centers. An intermediate mass black hole pulling in gas could easily account for the tremendous X-ray luminosity of a ULX without exceeding its Eddington limit. Finding such an object would be a monumental discovery, providing a crucial missing link in our understanding of how the supermassive black holes in galaxies first formed and grew. The second major hypothesis suggests that ULXs might be stellar mass black holes after all, but ones that are behaving in an extraordinary way. These could be what astronomers call microquasars binary systems, where a black hole or neutron star is feeding from a companion star at an incredibly high rate, forming a thick, puffy accretion disk. In this scenario, the black hole might be super Eddington, consuming material so voraciously that the accretion disk becomes unstable and bloated. This dense, thick disk could then focus the intense X-ray radiation into powerful beams like a cosmic lighthouse. If one of those beams is pointed directly at us, the source would appear much brighter than it truly is, creating the illusion of an ultra-luminous object. This beaming effect would mean we are seeing a kind of optical illusion, a trick of perspective that amplifies the apparent power of what is otherwise a relatively normal stellar remnant. The presence of these ULXs in the Sombrero Galaxy adds another layer to their mystery. This galaxy, with its strangely quiet central black hole, is not an environment we would expect to foster such extreme phenomena. ULXs are often associated with regions of vigorous star formation, like the spiral arms of other galaxies, where short-lived massive stars are constantly being born and dying, providing a ready supply of black holes and fuel. The Sombrero, by contrast, has very little ongoing star formation, especially in its prominent bulge where at least one of these ULXs has been detected. Finding such an energetic object in a relatively quiet, elderly stellar neighborhood is like discovering a raging bonfire in a library reading room. It's completely out of place. This forces astronomers to consider alternative formation mechanisms. Perhaps these ULXs are not young objects at all, but ancient systems that have been dynamically ejected from dense star clusters. Or maybe they are the remnants of past mergers, wandering intermediate mass black holes that were once the centers of devoured dwarf galaxies. Each ULX in the Sombrero is a unique clue. By studying their precise locations, their X-ray spectra, and how their brightness flickers over time, we can start to distinguish between the competing theories. Their very existence challenges our models of how black holes form and feed, demonstrating that even in a galaxy that appears calm and mature, there are pockets of extreme and violent activity that push the boundaries of known physics. Stepping back from the intense pinpoint sources of X-ray light, we confront a mystery on a far grander scale, one that concerns the very neighborhood of the Sombrero Galaxy itself. Our 11th strange object is defined not by what we see, but by a profound and puzzling absence. According to our most successful models of the universe, a galaxy as massive and dark matter-rich as the Sombrero should be the centerpiece of a bustling cosmic metropolis. Like a planet with a family of moons or a city surrounded by smaller towns, it should be orbited by a substantial entourage of dwarf satellite galaxies. These are small, faint collections of stars and dark matter that are gravitationally bound to their larger host. Our own Milky Way has over 50 known satellites, and the nearby Andromeda Galaxy has even more. Cosmological simulations based on the lambda-cold dark matter model consistently predict that a halo as massive as the Sombrero's should be teeming with hundreds of these tiny galactic companions. Yet, when astronomers point their telescopes toward the Sombrero, they find a startlingly quiet and empty frontier. Only a handful of potential dwarf satellites have been tentatively identified, a number that falls dramatically short of what theory demands. This discrepancy is more than just a minor accounting error. It represents a significant challenge to our understanding of how structure forms in the universe, making the void around the Sombrero one of its most compelling and unsettling features. So, where did all the satellites go? Astronomers are investigating several compelling explanations, each with far-reaching implications. The first and most straightforward possibility is that the satellites are indeed there, but they are simply too faint for our current telescopes to detect. Dwarf galaxies, especially those that are ancient and have undergone little star formation, can be incredibly diffuse. Their stars spread so thin that they blend seamlessly into the background glow of the night sky. They are cosmic ghosts present but invisible. Future observatories like the Nancy Grace Roman Space Telescope or the Vera C. Rubin Observatory, with their vastly improved sensitivity, may finally reveal this hidden population, solving the mystery by showing that the satellites were just hiding in plain sight all along. A second, more dramatic scenario suggests that the satellites are missing because they have already been destroyed. Given the evidence we've already seen for the Sombrero's cannibalistic past, this is a very real possibility. The immense gravitational pull of a large galaxy creates powerful tidal forces. If a dwarf satellite ventures too close on its orbital path, it can be stretched and torn apart, its stars shredded into long, faint streams that eventually merge into the main galaxy's halo. The Sombrero, with its unusually large population of globular clusters, may have been an exceptionally efficient predator, having already consumed its entire family of satellite galaxies over the past several billion years. The thousands of globular clusters we see today could be the sole survivors of this galactic feast, the only remnants of satellite systems that were completely devoured. In this view, the quiet emptiness around the Sombrero is not a sign of a quirk of nature, but a testament to its violent and thorough dominance over its local territory. Perhaps the most profound explanation, however, is that the missing satellites point to a flaw not in our observations but in our fundamental theories. The lambda cold dark matter model predicts that large dark matter halos should be filled with countless smaller subhalos, the gravitational wells that are supposed to attract gas and form dwarf galaxies. If the satellites are truly absent, it could mean that many of these dark matter subhalos failed to ignite star formation. This might be because the intense ultraviolet radiation from the early Sombrero Galaxy or from other nearby galaxies could have heated the gas in these small halos, preventing it from cooling and collapsing into stars. They would remain as completely dark halos, invisible structures of pure dark matter orbiting the galaxy, their presence only inferable through their subtle gravitational effects. An even more radical idea is that the properties of dark matter itself might be different than we assume. Perhaps dark matter particles interact with each other more strongly than we think, which would smooth out the small-scale clumpiness of the dark matter halo, reducing the number of subhalos that can form. The void around the Sombrero Galaxy thus becomes a critical testing ground for the very nature of the universe's most dominant but elusive component. This absence forces us to question whether we fully understand the intricate dance between dark matter and visible matter that builds the cosmic structures we see. The missing satellites are a silent challenge, a cosmic puzzle where the lack of evidence is itself the most compelling evidence of all. The gravitational fingerprints of the Sombrero's violent history are not limited to its swarm of globular clusters. They are also stamped across the very foundation of its starlight. Our 12th strange object is the galaxy's vast, diffuse stellar halo, a sphere of ancient stars that envelops the entire visible structure. Unlike the bright, concentrated bulge or the elegant disk, this halo is incredibly faint, a ghostly cloud of stars so spread out that mapping it is one of the most challenging tasks in modern astronomy. If the main galaxy were a brilliant city at night, this halo would be the dim, sprawling suburbs extending far out into the countryside. For a long time, it was assumed that such halos were roughly spherical, a natural consequence of a galaxy forming from a collapsing cloud of gas. But when astronomers meticulously charted the distribution of stars in the Sombrero's halo, they found something profoundly unexpected. It is not symmetrical. It is lopsided, stretched and pulled into an asymmetric shape, with one side appearing significantly more extended and populated than the other. This is not a minor imperfection. It is a fundamental distortion that reveals the galaxy did not form in peaceful isolation. A perfectly smooth, spherical halo is the signature of a quiet, undisturbed life. A twisted, uneven halo is the unmistakable scar of a lifetime of cosmic violence. This asymmetry is a fossil record, a billion-year-old crime scene where the evidence is written in the paths of countless stars. The most compelling explanation for this lopsidedness is a process called hierarchical accretion. The prevailing theory of galaxy formation holds that large galaxies like the Sombrero were built over time by consuming countless smaller dwarf galaxies. Each time a dwarf galaxy is captured by the immense gravity of a larger neighbor, it is torn apart. Its stars are not immediately assimilated into the orderly disk. Instead, they are scattered into a vast cloud, following chaotic, looping orbits that can take billions of years to settle. If these accretion events happen from all directions evenly over time, the resulting halo should be roughly spherical. But if a galaxy has recently devoured several satellites from a particular direction, or if it consumed one particularly large dwarf galaxy, the new stars will be added asymmetrically, creating a lumpy, uneven distribution that can persist for eons. The Sombrero's lopsided halo strongly suggests that its most recent meals arrived from a specific path in the sky. dumping a large amount of stellar debris onto one side of the galaxy and permanently skewing its equilibrium. We can think of this process like adding ink to a glass of water. If you add a single drop, it will slowly diffuse and create a uniform color. But if you pour a steady stream of ink into just one side of the glass, that side will remain noticeably darker and more concentrated for a long time. The sombrero's halo is that glass of water with the ink of devoured galaxies still not fully mixed. By studying the motions and chemical compositions of the stars in the extended part of the halo, astronomers can act as galactic archaeologists, tracing these stellar streams back to their original homes. Many of these stars will have different ratios of heavy elements, what astronomers call metallicity, compared to the stars native to the sombrero's main disk. Dwarf galaxies, with their simpler star-forming histories, often host stars that are more pristine with lower metallicities. Finding pockets of these ancient metal-poor stars in the lopsided part of the halo would be the smoking gun, confirming that they are indeed immigrants from smaller, devoured systems. This distorted halo does more than just confirm a violent past. It actively shapes our understanding of the sombrero's present and future. The gravitational pull of this lopsided mass exerts a constant, subtle torque on the inner galaxy, potentially contributing to the warping of the iconic dust lane we discussed earlier. It also provides a crucial link to the mystery of the missing dwarf satellites. The sheer size and asymmetry of the halo imply that the sombrero has been an efficient predator. It's possible that the reason we see so few satellites today is that the galaxy has already completed its feast, having long ago pulled in and digested the majority of its cosmic companions. The lopsided halo is the leftover evidence of that completed banquet. Furthermore, this structure blurs the line between the sombrero and its environment. The outermost stars of the halo are so tenuously bound that they essentially form a bridge between the galaxy and the intergalactic medium, a region where the galaxy's influence gradually gives way to the emptiness of space. This makes the halo a dynamic frontier, not a static boundary. The Sombrero Galaxy, then, is not a discrete, isolated island. It is a sprawling stellar empire whose true extent is hidden in a faint, lopsided cloak of ancient stars, each one a silent witness to the chaotic and building block nature of cosmic evolution. Yet the most dramatic evidence for a past cosmic collision may not lie in the lopsided halo or the warped disk, but in a structure that encircles the galaxy at a right angle to everything else. Our 13th strange object is the tantalizing evidence for a polar ring, a vast, faint loop of stars, gas, and dust orbiting the sombrero's main body over its poles, perpendicular to the familiar plane of the disk. Imagine the main galaxy as a spinning plate. A polar ring would be like a giant hula hoop spinning around the plate's edge, standing on its side. This kind of structure is one of the rarest and most spectacular sights in the universe, and its potential presence around the sombrero would be the single most telling clue about a specific catastrophic event in its past. While not yet definitively confirmed, observations have revealed faint streams and arcs of material at these extreme angles, hinting that a full polar ring might be there waiting to be fully mapped. The formation of a polar ring is a story of galactic violence and gravitational gymnastics on an epic scale. It does not form from a quiet, internal process. It is the direct result of a very particular kind of merger. The most widely accepted scenario begins with two galaxies, a large primary galaxy like the Sombrero and a smaller, gas-rich dwarf galaxy. For a polar ring to emerge, this smaller galaxy must be captured into a very specific orbit, a polar orbit, which means it circles the larger galaxy, passing directly over its north and south poles. As the dwarf galaxy makes these repeated close passes, the immense tidal forces from the large galaxy's gravity begin to shred it, but instead of the debris scattering randomly, something remarkable happens. The gas, dust, and stars from the doomed dwarf are stretched out along its original orbital path. Because that path was perpendicular to the main disk, the debris forms a new ring, a cosmic memorial to the vanquished galaxy, spinning in a plane 90 degrees off from the rest of the sombrero. This process can take hundreds of millions of years, and the ring itself may be a temporary structure, eventually settling into the main disk or dispersing entirely. Its very existence is a snapshot of a recent and incredibly precise act of galactic cannibalism. Confirming a polar ring around the sombrero would be a monumental discovery for several reasons. First, it would provide the clearest possible explanation for many of the galaxy's other oddities. The warped dust lane we encountered earlier could be a direct consequence of the gravitational disturbance caused by the infalling dwarf galaxy and the subsequent formation of the polar ring. The gravitational pull from this massive, perpendicular structure would constantly tug on the main disk, inducing the precise kind of wobbling and twisting that we observe. Furthermore, the lopsided stellar halo could be explained by this single, significant accretion event, which dumped a huge amount of stellar debris into a specific orbital plane. It would tie multiple mysteries into one neat, catastrophic bow. Second, a confirmed polar ring would solidify the sombrero's status as a hybrid galaxy. It would be undeniable proof that the beautiful spiral disk we see is not the whole story. It is a galaxy that has undergone a radical transformation, incorporating material from an entirely different plane of existence. This makes the sombrero a crucial case study for understanding how galaxies can evolve through mergers, not just to grow larger, but to change their fundamental shape and structure. Perhaps the most exciting implication involves the fate of the gas within the ring. Polar rings are often rich in hydrogen gas, the raw fuel for star birth. As this gas orbits high above the galaxy's main plane, it can be compressed during its journey, potentially triggering the formation of new stars in a completely isolated environment. We could see star clusters and stellar associations forming in this bizarre perpendicular ring, creating a second, fainter generation of stars that live their entire lives orbiting in a completely different direction from the billions of stars in the main disk. Finding such stellar nurseries would be the ultimate confirmation of the ring's existence and a stunning demonstration of how galactic collisions can create entirely new and isolated ecosystems for star formation. The search for this polar ring is ongoing, requiring incredibly deep observations to tease its faint glow from the background darkness. Its potential presence serves as a powerful reminder that the universe often hides its most dramatic stories in the faintest of details, and that a galaxy's true history is written not just in its bright center, but in the ghostly archives that surround it. Journeying inward from the galaxy's faint outer halo, we arrive at the very substance of the sombrero itself, its stars. To understand a galaxy's life story, astronomers often turn to chemical forensics, analyzing the composition of its stellar populations. This brings us to our 14th strange object, a characteristic that isn't a physical entity but a pervasive chemical pattern known as the metallicity gradient. In most large spiral galaxies, we observe a smooth and predictable change in chemical composition from the center outward. The galactic core, having undergone intense and rapid star formation for billions of years, is a crucible of heavy elements. Countless generations of stars have lived and died there, each one forging elements like iron, oxygen, and silicon in their nuclear furnaces and scattering them into space when they explode as supernova. This enriches the central regions, making the stars there metal-rich. As you move out along the spiral arms, the pace of star formation historically slows, and the enrichment from supernova is more diluted. Consequently, the stars in the outer disk tend to be more pristine, with a lower abundance of these heavy elements, making them metal-poor. This creates a gentle, sloping gradient, a smooth chemical transition from a metal-rich core to a metal-poor outskirts. The Sombrero Galaxy, true to its enigmatic nature, blatantly defies this expectation. Its metallicity gradient is not a gentle slope, it is startlingly steep and somewhat irregular. The drop-off in heavy elements from the brilliant bulge to the outer edge of the disk is dramatically sharp. It's as if the galaxy's chemical history is sharply divided, with a clear boundary separating a zone of extreme enrichment from a vast region that has remained curiously undeveloped. This anomaly is a profound clue, pointing to a history where the processes of star formation and metal distribution were anything but smooth and continuous. A steep gradient like this suggests that the inner and outer regions of the Sombrero have experienced vastly different evolutionary paths, almost as if they were two separate galaxies that have been awkwardly stitched together. What could cause such a chemical discontinuity? The most compelling explanation ties directly into the galaxy's potential hybrid origin. If the Sombrero formed from the merger of two galaxies, one large and one smaller, the violent gravitational interaction would have profoundly disrupted the orderly process of star formation. During a merger, gas clouds are thrown into chaos, colliding at high speeds. This can trigger a ferocious burst of new star formation in the central regions, rapidly consuming the available gas and creating a super-enriched core in a relatively short period. Meanwhile, the gas in the outer disk might have been stripped away entirely by tidal forces or pushed out to such large radii that it became too diffuse to collapse and form stars efficiently. The result is a galaxy with a core that has lived a fast and furious chemical life. While its outer reaches have been largely frozen in time, their gas reservoirs untouched and unenriched for eons. The sharp gradient is the lasting chemical signature of this galactic trauma. Another possibility involves the unique structure of the Sombrero itself. That massive, prominent bulge is more characteristic of an elliptical galaxy than a spiral. Elliptical galaxies often show very little metallicity gradient because their stars formed quickly and early in a chaotic, largely spherical collapse, mixing the elements more thoroughly. The Sombrero's immense bulge may have formed in a similar, rapid burst, creating a concentrated pool of metal-rich stars. Later, a separate event, perhaps the acquisition of a gas-rich companion, could have provided the raw material that settled into a thin, rotating disk around this pre-existing bulge. The stars that then formed in this new disk would have originated from gas that was already metal-poor, creating a stark chemical contrast with the ancient, enriched bulge. The steep gradient, in this case, is a record of two distinct epochs of star formation: an early, frantic period that built the bulge, and a later, more quiescent phase that formed the disk from relatively pristine material. This chemical fingerprint provides some of the strongest supporting evidence for the Sombrero's transitional nature, bridging the gap between spiral and elliptical galaxies. It's a silent narrative written in the elemental composition of billions of suns, telling a story of a galaxy whose development was abruptly interrupted and reshaped by forces beyond its control. This very chemical history we've just traced leads us directly to one of the most fundamental contradictions of the Sombrero Galaxy, a paradox that defines its hybrid nature. Our 15th strange object isn't a single entity you can point to, but a pervasive condition affecting its vast spiral disk. It's the mystery of the red and dead regions. When we look at a typical spiral galaxy like our own Milky Way or the magnificent Andromeda, we expect to see clear signs of vibrant youth. Their spiral arms are dotted with the brilliant blue light of massive, hot, young stars and the glowing pink nebulae of stellar nurseries where new suns are being born. This is the hallmark of a living, breathing galaxy. The Sombrero, for all its stunning spiral appearance, tells a very different story in many of its outer regions. While it does possess some areas of ongoing star formation, particularly associated with its dust lane, large swaths of its disk are eerily quiet. These zones are dominated by the dull, red glow of ancient, cooler stars. They are, in the parlance of astronomers, red and dead, a term usually reserved for giant elliptical galaxies that exhausted their gas supplies billions of years ago and have seen no new star birth since. Finding such extensive quiescent regions within a galaxy that still clearly possesses a disk structure is deeply unusual. It's as if the Sombrero is a living organism that is partially frozen in time, with one part of its body still active while another has entered a state of senescence. Why would a galaxy with such a prominent disk, a structure that should be a perfect cradle for star formation, show these signs of premature aging? The answer lies in a critical shortage of the essential ingredient for making stars: cold, dense molecular gas. Stars are born when vast clouds of this gas, primarily hydrogen molecules, collapse under their own gravity. For this to happen, the gas must be cool enough to clump together. Observations have shown that the Sombrero's disk is remarkably depleted in this cold gas, especially when compared to other spirals of similar size. The question then becomes, what happened to all the fuel? One of the prime suspects is the galaxy's own central engine, the supermassive black hole. Even in its current quiet state, it may have had a more active past. During an active phase, an enormous amount of energy would have been released from the core in the form of radiation and powerful jets. This phenomenon, known as AGN feedback, can have a catastrophic effect on a galaxy's gas reserves. The intense radiation can heat the galactic gas, preventing it from cooling and collapsing into stars. Even more effectively, those high-speed jets can blast through the disk, physically pushing huge quantities of cold gas out of the galaxy entirely, or heating it to such high temperatures that it becomes useless for star formation. It's a form of galactic self-regulation gone awry. The black hole, in its past fury, may have effectively sterilized large portions of its own home, shutting down the very process that defines a spiral galaxy. But the black hole might not be the only culprit. The Sombrero's history of galactic mergers likely played a decisive role. When galaxies collide, the event can trigger two opposing outcomes. In some cases, the collision compresses gas clouds, leading to a spectacular burst of star formation. In other cases, particularly if the merger involves galaxies with specific geometries and gas content, the process can be incredibly destructive. The gravitational turmoil can strip a galaxy of its gas or funnel it rapidly into the central regions, where it is either consumed by the black hole or used up in a single, frantic starburst. The outer disk, having been robbed of its fuel, is left high and dry. This strangulation scenario is a strong possibility for the Sombrero. Its past cannibalism of smaller galaxies may have provided the stars that now populate its massive halo and globular cluster system, but the violent dynamics of those mergers could have efficiently removed or consumed the cold gas reservoir needed to sustain star formation in the disk over the long term. The galaxy's immense dark matter halo also contributes to this strange state. The gravitational pressure from this massive, invisible envelope can heat the gas in the disk, making it more difficult for it to cool and form stars. This creates an environment where star formation is suppressed on a global scale, leading to the large red and dead patches we observe. This unique combination of a classic spiral structure with an elliptical galaxy's star-forming quiescence is what solidifies the Sombrero's status as a true hybrid or lenticular galaxy. It's a cosmic chimera, a celestial object caught between two evolutionary states. The presence of the disk shows that it once had the ordered rotation of a spiral, but the red and dead characteristics signal that its internal engine of creation has largely shut down. This makes the Sombrero a critical case study for understanding galactic mortality. It demonstrates that the transition from a vibrant, star-forming spiral to a quiet, aging elliptical isn't necessarily a sudden, violent event, but can be a gradual process of quenching. The galaxy isn't dead. It's in a state of arrested development, its beautiful spiral arms serving as a fossilized blueprint of a structure that no longer serves its original purpose. This strange duality forces us to reconsider the simple classifications we use for galaxies and reminds us that they are dynamic systems whose present appearance is just a single frame in a billion-year-long movie of birth, interaction, and slow decline. Yet the most ghostly remnants of the sombrero's past feasts are not found within its bright disk or even its lopsided halo, but etched across the darkest reaches of its surroundings as faint, arching brushstrokes of light. Our 16th and 17th strange objects are a pair of these celestial apparitions known as tidal streamers. These are not compact objects but vast, ribbon-like structures composed of stars that were once the hearts of small galaxies. They stretch for tens of thousands of light-years, tracing graceful, looping orbits that extend far beyond the sombrero's visible edge. To the most powerful telescopes, they appear as faint, shimmering rivers of starlight, so diffuse that their individual stars are barely distinguishable from the background glow of the universe. They are the skeletal remains of dwarf galaxies that ventured too close to the sombrero's immense gravitational pull. Over billions of years, the difference in gravity between the near and far sides of the dwarf galaxy, the tidal force slowly stretched it like cosmic taffy, pulling it apart until its stars were strung out along its entire orbital path. What we see today is the final act of this destruction, a ghostly orbit that marks the grave of a vanished galactic system. These streamers are far more than just beautiful relics. They are incredibly powerful forensic tools for galactic archaeologists. By carefully mapping the exact path, density, and speed of the stars within a tidal stream, astronomers can perform a form of celestial detective work, rewinding the clock billions of years to reconstruct the crime itself. The shape of the stream reveals the precise orbit the dwarf galaxy followed as it was consumed. The density of stars along the stream tells us about the original mass and size of the victim. Perhaps most importantly, the velocity of the stars within the stream acts as a direct probe of the sombrero's gravitational field, all the way out to these incredibly remote distances. Since gravity is a direct function of mass, measuring how stars accelerate along these streams allows scientists to create a precise map of how much mass is contained within their orbits. This is the key to weighing the galaxy's immense and otherwise invisible dark matter halo. The tidal streams are like cosmic scales. Their very existence and structure provide the most compelling evidence for the amount and distribution of the dark matter that dominates the sombrero's gravitational influence. The presence of not just one, but multiple tidal streams around the sombrero is a clear indicator of a long and violent history of hierarchical growth. Each stream represents a separate meal, a distinct chapter in the galaxy's life story. One stream might be long and well mixed, its stars nearly blended into the general halo, indicating a merger that occurred in the very distant past. Another might be brighter, sharper, and more confined, suggesting a more recent accretion event where the stars have not yet had time to disperse. By studying the chemical compositions of the stars in different streams, astronomers can even determine the type of galaxy that was devoured. Stars from a dwarf spheroidal galaxy, for instance, will have a much lower abundance of heavy elements compared to stars from a more evolved dwarf irregular galaxy. This allows scientists to piece together a family tree of the sombrero's victims, understanding not just how many galaxies it has consumed, but what kind of galaxies they were. These faint arcs are therefore a dynamic archive, a living record of the galaxy's assembly history that is still unfolding overhead. They transform the seemingly static image of the sombrero into a dynamic scene of ongoing gravitational interaction, where the ghosts of the past continue to swirl around the victor, telling their stories to anyone with the technology to listen. Delving deeper into the galaxy's structural heart, we encounter a feature that challenges our most basic assumptions about galactic stability. The 18th strange object is the subtle but significant suggestion of a misaligned central bar. In many spiral galaxies, including our own Milky Way, the central bulge is not a simple sphere of stars but is elongated into a bar-like structure. These bars are natural phenomena, forming over billions of years from instabilities within the rotating disk of stars. As stars orbit the galactic center, their collective gravitational pull can amplify small asymmetries, eventually organizing into a stable, elongated bar that rotates as a solid entity, perfectly aligned with the plane of the disk. This bar acts as a cosmic traffic regulator, funneling gas and dust from the outer regions inward toward the nucleus, often fueling star formation and feeding the central black hole. A well-aligned bar is a sign of a mature, dynamically settled galaxy, one that has achieved a long-term equilibrium. The potential bar in the sombrero, however, appears to defy this orderly picture. High-resolution studies indicate that if a bar exists, it is not only relatively small and weak compared to the galaxy's massive bulge, but it also seems to be tilted or misaligned with respect to the main disk. This is a profoundly strange configuration. A misaligned bar is inherently unstable. The overwhelming gravitational pull of the rest of the disk should, in a relatively short cosmic timescale, force it to snap into alignment. The fact that we might be seeing it in a skewed orientation is a powerful clue that the galaxy's inner dynamics have been recently and violently disturbed. It's as if we're looking at a gyroscope that is still wobbling back to stability after a sharp knock, telling us that the knock happened not so long ago. The most plausible explanation for this cosmic misalignment is a significant gravitational interaction, the same event that may have created the potential polar ring or warped the dust lane could be responsible. As a smaller galaxy passed by or merged with the sombrero, its gravitational tide would have washed over the entire system, but the effects would be most pronounced on the most delicate structures. A central bar, while dense, is a precise gravitational construct. A strong external pull can torque it out of its stable alignment, setting it into a slow precession. The persistence of this misalignment suggests the perturbing event occurred recently enough that the bar has not yet had time to settle back down. We are witnessing a temporary state of disequilibrium, a frozen moment in a slow-motion process of realignment that will take millions of years to complete. This provides a unique opportunity to study the resilience of galactic structures and the lasting impact of gravitational encounters. The misaligned bar is not just a curiosity, it is a ticking clock allowing us to estimate the timing of the sombrero's last major cosmic interaction and understand how galaxies physically respond to such profound disturbances. While these faint streamers and the misaligned bar testify to the galaxy's large-scale gravitational dramas, some of the most extreme evidence of violence is written in the trajectories of individual stars. Our 19th strange object is a cosmic fugitive, a star moving with such incredible speed that it is destined for intergalactic exile. This is a hypervelocity runaway star, a stellar projectile flung from the Sombrero Galaxy at a speed that defies its immense gravitational pull. Imagine a single star, a pinpoint of light, not peacefully orbiting within the galactic disk, but blazing a trail directly away from the galaxy, moving so fast that it will never return. Its velocity is so great that it exceeds the galaxy's escape velocity, meaning the combined gravitational pull of every star, every gas cloud, and the entire dark matter halo is insufficient to reel it back in. This star is on a one-way trip into the eternal blackness of intergalactic space, a lonely voyager cast out from its home. The existence of such an object within the sombrero transforms our view of the galaxy from a stable system to a cosmic particle accelerator, capable of launching its own constituents into the void with unimaginable force. The creation of a hypervelocity star requires an event of almost unimaginable power. Astronomers have identified two primary mechanisms, each a testament to the violent forces at play in dense galactic environments. The first and most dramatic scenario involves a close gravitational encounter with the supermassive black hole at the galaxy's center. This is known as the Hill's mechanism. Picture a binary star system, two stars orbiting each other closely as they wander too near the billion solar mass monster. The black hole's immense tidal forces can brutally tear the binary pair apart. One star is captured into a tight, often doomed orbit around the black hole, while the other is slingshotted away at a tremendous fraction of the speed of light. It's a gravitational slingshot effect on a colossal scale, using the black hole's gravity as a launch pad to fling a star across the galaxy and beyond. This process effectively converts the orbital energy of the binary system into the kinetic energy of the ejected star. For this to happen in the Sombrero, the star would have had to make an incredibly precise and close pass to the black hole, a rare but statistically possible event given the billions of stars swirling in the dense central bulge. The second major mechanism originates not from the galactic center, but from the intense environments of dense star clusters. In these crowded stellar cities, complex gravitational interactions between multiple stars can occur. Sometimes a binary star system can have a close encounter with a more massive star or another binary. During this chaotic gravitational dance, one of the stars can be ejected at high speed while the other participants absorb the recoil. While these ejections are typically not as fast as those from a black hole slingshot, they can still be powerful enough to reach escape velocity, especially from a cluster already orbiting in the outer regions of the galaxy where the galactic grip is weaker. Additionally, the supernova explosion of one star in a tightly bound binary system can act like a natural cannon. When the more massive star explodes, it can suddenly lose a significant amount of mass, drastically weakening the gravitational bond holding the pair together. If the explosion is asymmetric, it can kick the remnant, a neutron star or black hole, away at high speed. Its companion, now suddenly freed from its orbital tether, recoils in the opposite direction, flying off like a stone from a sling. This supernova kick can also propel a star to hypervelocity speeds. Identifying a specific runaway star candidate within the Sombrero is an immense technical challenge due to the galaxy's great distance. It requires precisely measuring the radial velocity, the motion toward or away from us, of individual stars against the bright background of the galaxy, and then discerning if their motion is part of the galaxy's general rotation or a distinct high-speed trajectory. However, the very possibility of their existence adds a thrilling dimension to the Sombrero's story. Each hypervelocity star is a smoking gun, a direct piece of evidence for the extreme gravitational environments that must exist within the galaxy. A star ejected by the central black hole confirms the dynamic and dangerous nature of the core, while one flung from a cluster speaks to the frenetic activity within its stellar populations. These stars become unique probes as they travel. By tracing their paths backward, astronomers can potentially pinpoint their origin point, whether it was a specific cluster or the immediate vicinity of the black hole. Furthermore, as they journey through the galactic halo and into intergalactic space, they carry with them the chemical signature of their birthplace. A hypervelocity star is thus a celestial time capsule, preserving the composition of the region it formed in long after it has left everything behind. The existence of even one such object underscores that the Sombrero is not a serene collection of stars, but a dynamic arena where gravitational forces routinely reach extremes, capable of creating individual stars with enough kinetic energy to break free from an entire galaxy. As we shift our focus from the high-speed drama of runaway stars to the broader architecture of the galaxy's disk, we encounter a feature that speaks to the Sombrero's deep evolutionary history. Our 20th strange object is not a single bright landmark, but a subtle, ghostly pattern etched into the faint outer regions of the galaxy, the fossil spiral arms. When we look at a typical spiral galaxy, the arms are prominent, bright with young blue stars and glowing pink nebulae, tracing a clear pattern of ongoing creation. But in the Sombrero, especially in the outermost parts of its disk beyond the prominent dust lane, astronomers have detected faint, vestigial structures that resemble the faded echoes of spiral arms. These are not the vibrant, star-forming pathways we typically picture. They are more like pale imprints, arcs of older, redder stars that retain the gentle curve of a spiral pattern but lack the energetic spark of youth. They are the celestial equivalent of faint footprints preserved in stone, telling a story of a time when the galaxy's spiral structure was more pronounced and active. These fossil arms are a profound clue because they reveal that a galaxy's iconic shape is not permanent. Spiral arms are not fixed structures made of the same stars forever. Instead, they are thought to be density waves, moving patterns of compressed gas and stars that travel through the galactic disk like ripples on a pond. As this wave passes through a region, it squeezes interstellar gas, triggering the collapse of clouds and the birth of new, brilliant stars that light up the arm. The stars themselves, however, continuously orbit the galactic center, moving in and out of the arm pattern over time. What we perceive as a permanent arm is actually a temporary traffic jam of stars and gas, a region of heightened density that is constantly being replenished. The existence of fossil arms in the Sombrero suggests that this wave activity has significantly weakened or even ceased in these outer regions. The density wave may have passed through for the last time eons ago, leaving behind a population of stars that were born during that active period. These stars continue on their orbits, still tracing the ghost of the pattern they were born in. But without new star formation to highlight the structure, the arms have faded into near invisibility. The presence of these faint imprints strongly supports the idea that the Sombrero is a galaxy in transition, slowly evolving from a vibrant spiral into a more quiescent lenticular form. The process that is causing the inner disk to become red and dead, whether it's AGN feedback, a past merger, or the influence of the massive dark matter halo, is also effectively quenching the density wave mechanism in the outer disk. Without a steady supply of gas to compress, the wave cannot sustain itself, and the spiral pattern begins to dissolve. The fossil arms are the direct evidence of this quenching in action. They are the fading afterglow of the galaxy's spiral past. This makes the Sombrero a rare and valuable snapshot of galactic aging. We are seeing a frame in the slow-motion movie of a spiral galaxy's death, where the dynamic processes that define its youth are winding down, leaving only these ancient stellar pathways as a memorial to its former vitality. By studying the exact ages and compositions of the stars in these fossil arms, astronomers can essentially carbon date them, determining precisely when the last major wave of star formation swept through these outer regions and how long ago the galaxy's spiral heart began to slow its beat. While hypervelocity stars represent the most dramatic individual expulsions, the Sombrero Galaxy also harbors a hidden population of the universe's most extreme stellar remnants, objects so dense that a single teaspoon of their material would weigh billions of tons. Our 21st, 22nd, and 23rd strange objects are a trio of these enigmatic compact object candidates, each one a potential neutron star or stellar mass black hole that exhibits bizarre and unpredictable behavior. Detected not in visible light but through their intense flickering in X-ray and radio wavelengths, these points of energy defy easy classification, representing the mysterious afterlife of massive stars within the galaxy. A neutron star is the collapsed core of a giant star that wasn't quite massive enough to form a black hole, an object typically only about 12 miles across yet containing more mass than our Sun, spinning at incredible speeds and possessing a magnetic field trillions of times stronger than Earth. A stellar mass black hole is the ultimate endpoint, a gravitational singularity from which not even light can escape. Under normal circumstances, we can identify these objects when they are in a binary system, pulling gas from a companion star. As this stolen material spirals inward, it forms a superheated accretion disk that glows brilliantly in X-rays, creating a predictable and measurable signature. But the candidates within the Sombrero are anything but predictable. Their strangeness lies in their extreme variability. Unlike the steady, rhythmic pulses of a typical X-ray binary, these objects flare up and fade with an almost chaotic randomness. One might remain quiet for years, emitting a barely detectable trickle of energy, only to suddenly erupt in a violent outburst that increases its brightness 1,000-fold in a matter of days or even hours before just as rapidly subsiding back into obscurity. This flickering behavior is a significant puzzle. For a stellar remnant, the rate at which it consumes material dictates its energy output. A steady diet from a companion star should produce a relatively consistent glow. The wild fluctuations seen in these candidates suggest a highly unstable and turbulent feeding process. Perhaps the companion star is itself variable, like a pulsating giant, dumping huge but irregular amounts of gas onto the compact object. Alternatively, the accretion disk itself might be prone to instabilities, building up material until it reaches a critical point and then dumping it all onto the central object in a sudden, catastrophic avalanche, creating the observed flare. This makes them the cosmic equivalent of a geyser, building up pressure for long periods before unleashing a tremendous burst of energy. The difficulty in confirming their exact nature from a distance of 28 million light-years is immense. The flickering itself is a major obstacle. To understand an object, astronomers need to observe it across multiple wavelengths simultaneously. But catching one of these candidates during a brief flare with both X-ray and radio telescopes is a challenge of precise timing and luck. Even when we do, the resolution of our telescopes is such that what appears as a single point of light could, in reality, be a tight cluster of several different sources. The flickering we attribute to one object might be the combined, overlapping signal from multiple compact objects in a dense stellar environment, like trying to distinguish individual fireflies blinking in a distant jar. Furthermore, the key diagnostic that separates a neutron star from a black hole, the measurement of its mass, is nearly impossible to obtain for these isolated candidates without a clearly observable companion star whose orbit can be meticulously tracked. A neutron star has a strict upper mass limit, around 2 or 3 times the mass of the Sun. Collapse it any further and it becomes a black hole. Without that crucial mass measurement, we are left with probabilistic arguments based on the energy spectrum of the X-rays and the presence or absence of pulsations. Neutron stars, with their solid surface and insane rotation, often generate regular, lighthouse-like pulses of radiation as they spin. The absence of such pulses might point toward a black hole, but it's not definitive proof, as the beam might simply not be pointing in our direction. These 3 enigmatic objects are more than just curiosities. They represent the tip of a vast, hidden iceberg, the mysterious population of dead stars that lurk throughout the Sombrero Galaxy. Every massive star that has ever lived has ended its life as either a neutron star or a black hole. The galaxy's history of vigorous star formation in its bulge and disk means it should be teeming with millions of these stellar ghosts. Yet we can only detect the tiny fraction that are currently active, those that are feeding or are in a configuration that makes their presence known. The strange variability of these 3 candidates suggests that the behavior of this hidden population is far more diverse and dynamic than our simple models predict. They hint at a complex ecosystem of stellar death and rebirth, where the remnants of past stellar generations continue to interact with their environment in violent and unpredictable ways. Studying them offers a unique window into the final stages of stellar evolution and the extreme physics that govern matter under conditions impossible to recreate on Earth. Each flicker, each unpredictable flare, is a message in a bottle from a long-dead star, telling us about the turbulent and hidden life that continues within the beautiful, silent hat of the sombrero. Beyond the frenetic activity of individual stars and the fading echoes of spiral arms, the Sombrero Galaxy exerts its influence on a scale so vast it can warp the very fabric of the universe around it. This brings us to our 24th strange object, a phenomenon that is not part of the galaxy itself, but a ghostly signature of its immense gravitational power, the potential gravitational lensing arc. According to Einstein's theory of general relativity, mass curves the space around it, and light, traveling in a straight line through this curved space, appears to bend. A massive object like a galaxy can act as a natural cosmic lens, distorting and magnifying the light from objects that lie far behind it. If a more distant galaxy is positioned almost perfectly behind the sombrero from our point of view, the sombrero's gravity should warp the distant galaxy's light, stretching it into a faint, thin arc or perhaps even a complete ring of light encircling the lensing galaxy. This effect, called strong gravitational lensing, is one of astronomy's most powerful tools, and the search for such an arc around the sombrero is a dedicated scientific pursuit. Discovering a lensed arc here, however, is exceptionally challenging. For the effect to be strong enough to create a visible arc, the alignment between the sombrero, the distant background galaxy, and our telescope must be incredibly precise. The sombrero, while massive, presents a specific problem for lensing because we see it almost perfectly edge-on. This means its mass is spread out along our line of sight, which can dilute the sharp, focused lensing effect needed to produce a bright, distinct arc. A more face-on galaxy would concentrate its mass into a smaller area on the sky, making it a more efficient lens. Furthermore, the background light source needs to be sufficiently bright and compact. If the galaxy behind the sombrero is too large or too diffuse, its lensed image will be a smeared and indistinct glow, nearly impossible to distinguish from the sombrero's own light. Astronomers must use the most sensitive telescopes, like the Hubble Space Telescope and the James Webb Space Telescope, to peer deep into the glare of the sombrero's bulge and disk, searching for these subtle, warped mirages. They are looking for a phantom, a signature of something that isn't there, its presence only revealed by the distortion it causes. The value of finding such an arc would be immeasurable, making it a truly strange and invaluable object. A gravitational lens is essentially a natural scale. The precise shape, brightness, and curvature of the lensed arc are direct consequences of the amount and distribution of mass in the foreground galaxy, the lens. By meticulously analyzing the arc's properties, astronomers could perform a direct geometric measurement of the sombrero's total mass, all the way out to the distance of the arc itself. This would provide the most accurate weight ticket ever obtained for the galaxy. Crucially, this measurement includes everything: the stars, the gas, and most importantly, the dark matter. It would allow scientists to map the dark matter halo with unprecedented precision, confirming its immense size and potentially revealing details about its shape, whether it is perfectly spherical or slightly flattened. This would be a critical test for the dark matter models we discussed earlier, offering real-world data to compare against the predictions of supercomputer simulations. A lensing arc would transform the sombrero from a subject of observation into a scientific instrument itself, a colossal cosmic lens that we can use to weigh the invisible and probe the geometry of the universe on the largest scales. The ongoing search for this phantom arc is a testament to the lengths we will go to understand the hidden forces that sculpt our cosmos, using the warping of light itself to illuminate the darkness. But the gravitational echoes of the sombrero's past are not confined to the ghostly streams of stars. They are also written in the very motion of the gas that courses through its system. Our 25th strange object is a celestial rebel, a massive cloud of hydrogen gas that defies the galaxy's fundamental rhythm by orbiting in the exact opposite direction to the vast majority of its stars. Imagine a vast, sprawling city where every car on the highway moves in a smooth, coordinated flow in one direction. Now, picture a massive fuel tanker barreling down the wrong side of the road against the tide of traffic. This is the cosmic equivalent of the counter-rotating gas cloud within the sombrero. This isn't a minor turbulence or a small eddy in the flow. It is a major structure, a significant reservoir of primordial material that moves with a profound and deliberate wrong-way momentum. Such a configuration is fundamentally unstable and cannot arise from the galaxy's natural internal evolution. a galaxy forms from a single, collapsing cloud of gas that conservation of angular momentum sets spinning in one dominant direction. For a cloud of this scale to be moving in reverse is a glaring signpost pointing directly to an external origin. This rebellious cloud is the undeniable forensic evidence that the Sombrero has recently consumed a foreign body, a gas-rich dwarf galaxy that entered the system on a drastically different retrograde orbit. The most likely story of this cloud's origin is a tale of galactic capture and digestion. Billions of years ago, a small, gas-rich dwarf galaxy on a specific, retrograde path, meaning it was orbiting the Sombrero in the opposite direction to the disk's rotation, ventured too close. The immense tidal forces of the larger galaxy began to shred the dwarf, pulling it apart. Its stars, being more tightly bound, were scattered into the halo, perhaps contributing to the lopsided structure we've already discussed. But its expansive envelope of cold hydrogen gas, being more diffuse, was stretched into a long stream. Over cosmic time, this stream of gas, still carrying the momentum of its original backward orbit, settled into a vast cloud or a disk-like structure within the main galaxy, but moving in the opposite direction. It's a case of cosmic indigestion. The Sombrero swallowed the dwarf, but it hasn't yet fully assimilated this gaseous component, which retains the orbital signature of its original home. This process of accretion from an external source is the only plausible way to inject such a massive amount of material with a counter-rotating motion into an otherwise orderly system. The cloud is a leftover, a piece of the victim that hasn't yet been mixed into the galactic whole. This backward motion, however, comes at a great cost. The cloud is not sailing through empty space. It is plowing against the flow of the galaxy's own interstellar medium. This creates immense dynamical friction, a gravitational drag force that acts like a cosmic brake. As the cloud moves against the background of stars and gas, its gravity tugs on them, creating a wake of slightly denser material behind it. This wake, in turn, exerts a gravitational pullback on the cloud, slowing it down. It's analogous to trying to walk through a crowded pool. Moving against the current requires much more effort and steadily robs you of your forward momentum. For the counter-rotating cloud, this friction is a relentless and inescapable force. Its orbit is not stable. It will gradually decay, losing energy and spiraling slowly inward toward the galactic center over hundreds of millions of years. This inward journey seals the cloud's ultimate fate. As it drifts closer to the core, it will encounter even denser regions of stars and gas, accelerating its decay. Eventually, this vast reservoir of fresh, cold fuel will be delivered directly to the inner regions of the galaxy, right into the vicinity of the supermassive black hole and the dense stellar population of the bulge. The eventual arrival of this rebellious cloud could trigger a dramatic transformation in the Sombrero's core. This infusion of new material could ignite a spectacular burst of star formation, lighting up the central regions with the blue light of newborn stars. More dramatically, it could provide the long-sought fuel to awaken the sleeping giant, the billion solar mass black hole. If even a fraction of this gas eventually spirals into the black hole's accretion disk, it could end the black hole's quiescent state, potentially turning it into a vibrant, active galactic nucleus with brilliant jets and intense radiation. The counter-rotating cloud, therefore, is not just a relic of a past collision. It is a ticking time bomb, a stored source of energy that could one day dramatically alter the galaxy's appearance and activity. Its present rebellion sets the stage for a future cataclysm, a final act of cosmic integration where the last remnant of a devoured galaxy will ultimately be consumed, potentially lighting a fire in the heart of the Sombrero that will shine across millions of light years. Now, as we turn our gaze from the grand, dynamic flows of gas to the intimate lives of individual stars, we encounter a paradox of age and appearance that seems to defy the very logic of stellar evolution. Our 26th strange object isn't a single star, but a peculiar class of them found in surprising numbers throughout the Sombrero's ancient star clusters, the blue stragglers. To understand their strangeness, picture a massive globular cluster, a dense ball of hundreds of thousands of stars that all formed together in a single, frantic burst over 10 billion years ago. In such an ancient stellar retirement home, you would expect to see only old, cool red stars, the massive, hot blue stars which burn through their fuel in just a few million years should have vanished eons ago, leaving behind their slower-burning, lower-mass siblings. Yet, scattered among these red ancients, astronomers spot brilliant blue stars shining with the vigor of youth. They are the stragglers, seemingly lagging behind their peers in the race toward stellar death, appearing billions of years younger than everything else in the cluster. The Sombrero Galaxy, with its immense population of globular clusters, appears to host an unusual overabundance of these celestial anomalies, making its clusters look strangely rejuvenated. The existence of blue stragglers poses a fascinating question. How can a star appear so young in such an old environment? They aren't actually young stars born recently. That's nearly impossible in the gas-poor environment of a globular cluster. Instead, they are old stars that have found a way to cheat death, or at least delay the inevitable signs of aging. Astronomers have two primary theories for how these stars pull off this cosmic deception, and both involve a level of stellar intimacy that is commonplace in the crowded cores of these clusters. The first theory is one of violent renewal, a stellar collision. In the incredibly dense downtown of a globular cluster, where stars can be thousands of times closer together than in our solar neighborhood, close encounters and direct collisions, while still rare, are far more likely. If two older, lower-mass stars slam into each other, they can merge into a single, more massive star. This new composite star has a fresh supply of hydrogen fuel at its core, effectively resetting its evolutionary clock. It now behaves like a much younger, hotter, and bluer star, even though its constituent parts are as ancient as the cluster itself. It's a stellar phoenix born from the wreckage of its predecessors. The second theory is more of a slow cosmic vampirism. Many stars in the universe are born in binary systems, two stars orbiting a common center of gravity. A blue straggler can form if one star in an aging binary system begins to swell into a red giant as it runs out of fuel. If its companion star is close enough, it can start to gravitationally pull the outer, hydrogen-rich layers off the giant and onto itself. This process, called mass transfer, feeds the smaller star, increasing its mass and reigniting its nuclear furnace with fresh hydrogen. The recipient star becomes hotter, brighter, and bluer, while the donor star is stripped down to its bare core. This creates the illusion of a young, blue star orbiting a strange, depleted stellar remnant. This is a gentler path to rejuvenation, a slow feast that transforms an old star into a brilliant blue straggler over millions of years. The true mystery in the Sombrero is not that blue stragglers exist, but that they seem to be so unusually common within its vast swarm of globular clusters. This overabundance is a significant clue about the unique conditions within these clusters. The key factor is density. Globular clusters with tighter, more densely packed cores are expected to produce more blue stragglers via collisions. The Sombrero's clusters, particularly the metal-rich ones that orbit closer to the galactic center, may be exceptionally dense, perhaps as a result of the galaxy's violent history. The gravitational tides from past mergers or close interactions with the galactic core could have compressed these clusters, driving their stars closer together and increasing the frequency of the dramatic encounters that create collision-born stragglers. Alternatively, the overabundance might tell us something about the binary star populations within the Sombrero's clusters. If a higher-than-average fraction of stars were born in binary systems billions of years ago, there would simply be more raw material available for the mass transfer process to create blue stragglers. The galaxy's unique formation history may have favored the creation and preservation of these binary systems. Studying this particular population of stars gives astronomers a powerful tool to understand the internal dynamics and life stories of the clusters themselves. The number and location of blue stragglers within a cluster act as a direct measure of its dynamical age. Over billions of years, a globular cluster relaxes and evolves. Heavier stars sink toward the center in a process called mass segregation. Because blue stragglers are more massive than the average cluster star, they too should migrate toward the core. Finding them scattered throughout a cluster rather than concentrated in the center can indicate a system that is still dynamically young and hasn't fully settled. The specific distribution of blue stragglers in the Sombrero's clusters could therefore reveal which clusters are ancient and relaxed and which have been recently shaken up by a close pass to the galactic center, an event that can dynamically rejuvenate a cluster by stirring up its stars. These seemingly misplaced blue stars are therefore more than just a curiosity. They are vital diagnostic tools, cosmic probes that illuminate the hidden gravitational interactions and the long, complex lives of the star clusters they call home. Their unusual prevalence in the Sombrero is one more piece of evidence that this galaxy's components have experienced a more dynamic and interactive history than we once believed. Yet another layer of complexity is woven into the fabric of the Sombrero Galaxy, one that is entirely invisible to our eyes but exerts a powerful influence on its structure. Our 27th strange object is the galaxy's intricate and surprisingly powerful magnetic field. Imagine the entire vast expanse of the galaxy threaded with an unseen web of magnetic force lines, like a colossal, invisible bar magnet stretched across tens of thousands of light years. While all large galaxies possess magnetic fields, the Sombrero's is particularly unusual. Observations, primarily through the polarization of radio waves emitted by cosmic rays spiraling along these field lines, reveal a configuration that is both remarkably ordered and unexpectedly strong, especially tracing the path of the iconic dark dust lane. This isn't a chaotic, tangled mess of magnetism. In these regions, the field lines are stretched and aligned with a degree of coherence that is rare for a spiral galaxy, creating a structured magnetic maze that channels and constrains the movement of interstellar material. The role of a galactic magnetic field is subtle but profound. It acts as a cosmic guide rail for the galaxy's gas and dust. When a cloud of gas begins to collapse under its own gravity to form a new star, the magnetic field can provide a supporting pressure that resists the collapse, effectively putting the brakes on star birth. For a star to form, the gas must somehow slip past these magnetic handcuffs, a process that often involves the slow, drifting neutral particles slipping through the ionized gas that is tied to the field lines. Furthermore, these fields can channel the flow of material, directing gas along specific pathways and influencing the large-scale dynamics of the interstellar medium. They can also confine and shape the spectacular bubbles and shells blown by supernova explosions, giving these structures their distinct forms. In the Sombrero, the discovery of such an ordered and strong field along the dust lane suggests it plays a critical role in the galaxy's current state of star formation or lack thereof. The field's strength could be one of the key factors helping to suppress new star birth in the disk, by providing that extra support against gravitational collapse and maintaining the gas in a more diffuse, stable state. The origins of such a well-ordered magnetic field point to dynamic processes deep within the galaxy's history. Galactic magnetic fields are thought to be generated and sustained by a dynamo effect, a process driven by the complex motions of ionized gas within the galactic disk. As the galaxy rotates, its charged particles swirl and shear, amplifying any small, primordial magnetic seed fields into the large-scale structures we observe today. The strange configuration in the Sombrero, however, suggests its dynamo has been influenced by extraordinary events. The most compelling explanation ties back to the galaxy's potential merger history. The violent gravitational turmoil of a galactic collision would have stirred the interstellar medium to a frenzy, creating immense turbulence and shear flows that could have supercharged the dynamo, rapidly amplifying the magnetic field and stretching it into its current highly ordered state. The field we see today could be a fossil imprint of that ancient violence, a magnetic memory of the chaotic forces that once rocked the galaxy. Alternatively, the strong field along the dust lane might be a direct result of the lane's own structure. The dense concentration of gas and dust in that region could be compressing the magnetic field lines, strengthening them and forcing them to align with the lane's geometry, much like pinching a bundle of rubber bands makes them more taut and parallel. This interplay between gravity, gas dynamics, and magnetism creates a feedback loop where the field shapes the gas and the gas, in turn, shapes the field. Understanding this magnetic maze is crucial because it adds a fundamental force to the narrative of the Sombrero's evolution. It is not just gravity and collisions that have sculpted this galaxy. The invisible hand of magnetism has also been a constant and powerful architect, guiding its gas, regulating its star formation, and leaving behind a strange, ordered signature of a turbulent past. But the collective power of stellar death doesn't just create individual stellar ghosts. It can also carve out vast, empty chambers in the fabric of the galaxy itself. Our 28th strange object is a colossal cavity known as a supershell supernova remnant. Imagine a single supernova explosion, the violent death of a massive star, which can blast a bubble in the interstellar medium dozens of light years wide. Now amplify that power. A supershell is what happens when an entire family of massive stars, born together in a dense cluster, lives out their short, brilliant lives and then dies in a rapid-fire sequence of supernova over a few million years. Each consecutive explosion adds its energy to the previous one, inflating a single, gargantuan bubble that can stretch for hundreds, even 1,000 light years across. Within the Sombrero Galaxy, astronomers have identified several of these immense structures, appearing as faint, arc-like rims or vast, dark voids when viewed in specific wavelengths of light that reveal the distribution of gas. They are not just empty spaces, they are the celestial equivalent of a clearing in a forest created by a chain of cosmic dynamite blasts. The formation of a supershell is a dramatic and coordinated event. It begins with the birth of a massive stellar nursery, a giant molecular cloud that gives rise to a cluster of O-type and B-type stars, the true giants of the stellar world. These stars are destined to live fast and die young, with lifespans of only a few million years. As they near the end of their lives, their powerful stellar winds begin to push against the surrounding gas, creating an initial cavity. Then the first star explodes. The supernova shockwave slams into the walls of this pre-existing bubble, heating the gas and driving it outward. Before the expanding shell has a chance to slow down and dissipate, another star in the cluster reaches its endpoint and detonates, injecting a fresh surge of energy. This process repeats itself, with each new explosion acting like a piston, relentlessly driving the shell to ever greater sizes. The resulting structure is a testament to the collective power of stellar mortality, a collaborative act of destruction on an epic scale that no single star could ever achieve alone. The impact of a supershell on its galactic environment is profound. As it expands, it acts as a powerful regulator and catalyst for future star formation. The immense shockwave sweeping through the interstellar medium can compress surrounding clouds of cold gas to critical densities, triggering the gravitational collapse that births a new generation of stars. In this way, the death of one group of stars can literally sow the seeds for the birth of the next, creating a self-propagating cycle of stellar life and death. The rim of the expanding shell often becomes a fertile ground for this triggered star formation, appearing as a bright ring of newborn stars and glowing nebulae. However, the supershell's influence is not solely creative. As it grows, it can also sweep up and expel a tremendous amount of gas from the galactic disk, potentially pushing it out into the halo or even ejecting it from the galaxy entirely. This process, known as galactic feedback, can effectively sterilize a large region of the galaxy, shutting down star formation for eons by removing the essential raw material. A single supershell can therefore both give life and take it away, its legacy written in the patterns of stellar clusters and the empty deserts of gas it leaves behind. The presence of such a large and well-defined supershell in the Sombrero Galaxy is particularly intriguing because it seems to contradict the galaxy's overall red and dead character in its outer disk. Finding evidence of a recent, coordinated burst of massive star formation suggests that, despite the general quiescence, there are still pockets of vigorous activity, or at least there were in the relatively recent cosmic past. The supershell's current size and expansion velocity allow astronomers to estimate when the chain of supernova that created it occurred. If the shell is still expanding rapidly, it points to a star-forming event that took place within the last tens of millions of years, a mere blink in galactic time. This forces a re-evaluation of the Sombrero's recent history. It indicates that the process of star formation shutdown has not been uniform or complete. Some reservoirs of cold gas must have persisted or been recently acquired, allowing for a final, dramatic burst of stellar activity. The supershell stands as a monument to this last gasp of creation, a final, defiant flare of stellar birth before the long slide into galactic old age. It is a fossilized bubble of energy, a ghostly imprint of a stellar family that lived and died together, whose collective final breath continues to shape the galaxy around it millions of years later. Lurking in the faint glow surrounding the Sombrero's brilliant disk is a faint, ethereal smudge of light that might be mistaken for a flaw in the image or a distant, unrelated galaxy. But this unassuming patch of luminosity is our 29th strange object, and it represents a celestial crime in progress. This faint smudge is almost certainly a dwarf satellite galaxy in its death throes, caught in the immense gravitational grip of the Sombrero and currently being stretched, pulled, and torn apart. Observing this object is like walking into a moment of cosmic violence frozen in time. We are witnessing the fundamental process of hierarchical galaxy growth happening right before our eyes, a process that is usually so slow it spans billions of years. For this doomed dwarf, the end is near, and its final moments are a strangely beautiful and violent ballet dictated by the relentless force of gravity. The mechanism of its destruction is a phenomenon with a vividly descriptive name, spaghettification. As the small galaxy ventures closer to the Sombrero, it experiences an extreme difference in gravitational pull across its body. The side of the dwarf galaxy facing the Sombrero feels a much stronger tug than the side facing away. This difference, known as a tidal force, acts like a cosmic puller, stretching the galaxy lengthwise. At the same time, the gravitational pull squeezes the galaxy from the sides, compressing it. The combined effect of this stretching and squeezing transforms the once roughly spherical dwarf galaxy into a long, thin stream of stars, gas, and dark matter. It's as if the galaxy is being drawn out into a filament, a strand of celestial spaghetti, its constituent stars being separated from one another and strung out along its orbital path. This process doesn't happen quickly. It can take hundreds of millions of years for a galaxy to be fully disrupted, but the faint, elongated shape of this object suggests we are catching it mid-disruption, a snapshot of a slow-motion disintegration. What makes this object so invaluable to astronomers is that it provides a real-time laboratory for studying a critical phase of galactic evolution that is normally only inferred from fossil evidence like tidal streams. We can observe the physics of tidal disruption as it happens. By measuring the exact shape and length of the stretched galaxy, scientists can calculate the strength of the tidal forces at work and thus better map the Sombrero's gravitational field at this great distance. They can study how the different components of the dwarf galaxy respond to the stress, The dark matter, which interacts only through gravity and not by electromagnetic forces, will be the first to be stripped away, forming a diffuse halo around the stream. The stars, being more tightly bound, will take longer to separate, and the gas will behave in its own complex ways, potentially forming knots and clumps as it is drawn out. Watching this process unfold allows us to test our models of galaxy structure and dark matter distribution with unprecedented directness. There is a profound duality to this object. It is both beautiful and brutal. The resulting tidal stream, as the galaxy is completely shredded, will eventually become a graceful, arching river of starlight, a delicate veil of luminosity adorning the sombrero. Yet its creation is an act of incredible violence, the utter annihilation of a galactic system. Each star within the dwarf galaxy is being gently, inexorably pulled away from its neighbors, its orbit permanently altered. For any hypothetical civilization within that dwarf galaxy, the experience would be apocalyptic, not with a sudden crash, but with a gradual, unstoppable stretching of their very sky as the host galaxy is dismantled around them. This ongoing destruction also solves a piece of the missing satellite puzzle we encountered earlier. The absence of many dwarf galaxies around the sombrero may not be because they never existed, but because the sombrero has been an efficient predator. This faint smudge is a living example of that predation, a current meal in the process of being consumed. Its eventual fate is to merge completely with the sombrero's halo, its stars becoming anonymous members of the larger galaxy's population, its identity forever erased. This strange, faint object is therefore a fleeting portrait of a galaxy's final moments, a transient stage in the cosmic food chain that highlights the dynamic and often destructive interactions that shape the universe we see today. And as we witness the final, violent act of a dwarf galaxy being consumed, we are reminded that our entire understanding of such cosmic distances relies on a delicate chain of measurement, a ladder built from specific celestial objects we believe we understand perfectly. This brings us to our 30th strange object, a class of stars that should be dependable guides but in the Sombrero Galaxy have begun to act strangely, the anomalous Cepheids variables. Cepheids are the linchpin of the cosmic distance ladder, the fundamental tool we use to measure the scale of the universe. These are pulsating giant stars that rhythmically brighten and dim over periods ranging from days to months. Crucially, there is a direct and powerful relationship between a Cepheid's pulsation period and its intrinsic brightness. The longer it takes to pulse, the more luminous it truly is. By simply measuring the period of its pulsation from Earth, astronomers can determine its true wattage. Then, by comparing that known intrinsic brightness to how dim it appears from our vantage point, they can calculate its distance with remarkable precision. This method is how we measured the distance to the Sombrero Galaxy itself, solidifying its place 28 million light-years away. But this entire elegant system collapses if the Cepheids themselves are not the perfectly predictable standard candles we assume them to be. Within the Sombrero, a number of these crucial stars are exhibiting subtle but significant misbehavior. Their pulsations are not quite aligning with the established period luminosity relationship. Some might be slightly too bright for their pulsation period, while others are inexplicably faint. At first glance, a discrepancy of even a small fraction of a magnitude might seem trivial, but in the precise world of cosmic cartography, it represents a potential crisis. A miscalibration of the standard candle used to measure a galaxy 28 million light-years away doesn't just throw off that one measurement. It introduces a ripple effect of error that can extend all the way out to the edges of the observable universe, impacting our measurements of the expansion rate of the cosmos and the nature of dark energy. So, what could be causing these trusted stars to become unreliable? One of the primary suspects is an issue of cosmic pollution, interstellar dust. The Sombrero Galaxy, with its massive and complex dust lane, is a particularly challenging environment for this kind of measurement. Dust particles scattered throughout space act like a fine fog, absorbing and scattering starlight, making distant objects appear dimmer and redder than they truly are, an effect known as extinction. If we fail to account for the exact amount of dust between us and a specific Cepheid, we will mistakenly think the star is farther away than it actually is. The problem is that dust is not uniformly distributed. It can clump in unpredictable ways. A Cepheid tucked behind an unusually dense knot of dust in the Sombrero's warped disk could be severely dimmed, throwing off our distance calculation. Correcting for this requires incredibly detailed maps of the galaxy's dust distribution, a task that is immensely difficult at such a great distance. The anomalous faintness of some Cepheids could therefore be a simple case of inadequate dust correction, a reminder that we are looking at these stars through a dirty and uneven window. A second, far more exciting possibility is that the anomaly points to a flaw in our fundamental understanding of the stars themselves. Our models of Cepheid pulsation are sophisticated, but they are based on a set of assumptions about the star's internal structure, composition, and mass. The Cepheids in the Sombrero might be challenging those assumptions. For instance, the metallicity of a star, the fraction of its composition made up of elements heavier than hydrogen and helium, can affect its pulsations. The Sombrero Galaxy, with its unusually steep metallicity gradient, hosts stars with a wide range of chemical compositions. A Cepheid born in the metal-rich bulge might pulsate differently than an identical twin born in the metal-poor outer disk. If our standard period luminosity relationship was calibrated using Cepheids with a certain metallicity, applying it to stars with a different chemistry could introduce a systematic error. Furthermore, the evolution of stars in the Sombrero's unique environment, perhaps influenced by its history of mergers or its intense central radiation field, might have produced Cepheids with different masses or ages than those we've studied in our own galactic neighborhood. These subtle differences in stellar pedigree could manifest as slight deviations in their pulsation behavior, revealing new physics about how these giant stars operate under diverse conditions. The resolution to this puzzle has profound implications that reach far beyond the boundaries of the Sombrero Galaxy. Astronomers are actively engaged in a fierce debate known as the Hubble tension, a disagreement over the precise value of the universe's expansion rate. Different methods of measuring this rate, some using Cepheids and others using the cosmic microwave background, are yielding slightly different answers. The strange Cepheids in the Sombrero are now key players in this high-stakes cosmological controversy. If their anomalies are due to a previously unknown complexity in the period-luminosity relationship, a complexity that varies from galaxy to galaxy, it could help explain the Hubble tension and lead to a recalibration of our entire cosmic distance scale. This would force us to rewrite chapters in our cosmology textbooks. Alternatively, if the anomalies are successfully explained by better dust mapping, it would solidify our confidence in Cepheids and intensify the mystery of the Hubble tension, pointing toward the need for new physics to explain the universe's expansion. Each anomalous twinkle of these distant stars is therefore a message, a piece of data in a debate that strikes at the heart of our understanding of the cosmos. They are strange not merely for being outliers, but for holding the potential to either confirm our fundamental models or reveal that our most trusted rulers for measuring the universe are slightly warped. Deep within the vast swarm of nearly 2,000 globular clusters that orbit the Sombrero Galaxy, two particular clusters stand out not for their brightness or size, but for the frantic, chaotic motion hidden within their dense cores. These are our 31st and 32nd strange objects, a pair of stellar cities where the stars are not moving in a calm, orderly fashion, but are instead zipping about with a startlingly wide range of velocities. Astronomers measure this internal frenzy with a property called velocity dispersion. In a typical, relaxed globular cluster, the gravitational pull of the entire cluster keeps most stars moving at roughly similar speeds, resulting in a low velocity dispersion. It's like a well-behaved crowd moving through a city square. But in these two specific clusters, the velocity dispersion is remarkably high, indicating that some stars are sluggishly drifting while others are hurtling through the core at breakneck speeds. This internal turmoil is a glaring sign that something massive and unseen is stirring the pot, dominating the gravitational landscape at the very heart of the cluster. So, what force could be whipping these stars into such a frenzy? The most compelling explanation is the presence of an intermediate mass black hole lurking at the center of each cluster. This would be a black hole of a class that has long been theorized but is incredibly difficult to confirm, with a mass between 100 and 100,000 times that of our Sun. It would fill the critical gap between the stellar mass black holes formed from collapsing stars and the supermassive giants that rule galactic centers. Imagine such an object anchored in the core of a globular cluster. Its immense gravitational pull would act like a cosmic magnet, accelerating any star that makes a close pass to tremendous velocities. Stars on wider, slower orbits would be largely unaffected, creating the exact high dispersion, mixed-speed environment we observe. The gravitational grip of an intermediate mass black hole would provide the central engine needed to explain the observed stellar motions, making these clusters miniature versions of the Sombrero Galaxy itself, each with its own hidden, massive heart. There is, however, another equally fascinating possibility for the origin of this strange velocity signature. These clusters might not be ordinary globular clusters at all, but the stripped cores of former dwarf galaxies. This concept, known as the threshing scenario, begins with a small dwarf galaxy orbiting the Sombrero. Over billions of years, the immense tidal forces from the large galaxy act like a cosmic grinder, peeling away the dwarf's outer layers of stars, leaving behind only its incredibly dense, resilient core. What remains is an object that looks to our telescopes very much like a globular cluster, but it is in fact the naked heart of a devoured galaxy. The crucial difference lies in the internal dynamics. The core of a dwarf galaxy is likely to be far denser and more massive than a typical globular cluster, and it may have already contained its own central black hole from its days as an independent system. This inherited density and potential black hole would naturally result in the high-velocity dispersion we see today. These strange clusters would therefore be celestial trophies of the Sombrero's cannibalistic past, not born within the galaxy but captured and devoured, their frantic inner motion a lasting echo of their former independence. Distinguishing between these two theories is a monumental challenge that pushes our observational capabilities to their absolute limits. To confirm an intermediate mass black hole, astronomers search for the telltale rising velocity dispersion in the innermost regions of the cluster. They painstakingly measure the speeds of individual stars, plotting how their velocities change as you approach the exact center. A sharp, continuous increase in velocity dispersion right down to the central arcsecond would be the smoking gun for a concentrated, massive object. They also look for the faint, flickering glow of X-rays that might be emitted if the black hole is actively pulling in gas from its surroundings, a faint whisper of accretion. On the other hand, evidence for the stripped nucleus theory comes from studying the cluster's chemical composition. If the stars within it show a distinct metallicity signature, a specific pattern of heavy elements, that is different from the native clusters of the Sombrero, it would strongly suggest an external origin. The stars would carry the chemical fingerprint of the smaller galaxy they originally called home. The existence of either scenario has profound implications. If these clusters do host intermediate mass black holes, they would provide the first solid evidence for these elusive objects and offer a potential solution to one of astronomy's biggest puzzles. How do supermassive black holes grow to such immense sizes? One leading theory is that they start as intermediate mass seeds and grow through mergers and accretion. Finding these seeds still residing in globular clusters would be a crucial piece of that evolutionary puzzle. Conversely, if these are stripped dwarf galaxy nuclei, they provide a direct and measurable link to the Sombrero's hierarchical growth, offering a way to weigh the properties of the long-vanished dwarf galaxies that were consumed. They would be individual data points in the galaxy's assembly history. These two high-velocity dispersion clusters, therefore, are far more than just strange curiosities. They are natural laboratories for studying extreme gravity and galactic evolution. Their internal chaos, a seemingly random jumble of stellar speeds, is in fact a precise record of the powerful forces, whether a hidden black hole or a traumatic origin, that have shaped their existence over billions of years. While the visible light portrait of the Sombrero presents a picture of serene, mature elegance, a view through the infrared eyes of telescopes like the Spitzer Space Telescope reveals a dramatic secret simmering just beneath the surface. Our 33rd strange object is not a single entity but a raging, hidden inferno, an infrared luminous region that betrays the presence of a powerful hidden starburst. Nestled within and around the galaxy's iconic dark dust lane, this area glows with an intense, surprising heat. That warmth isn't coming from the old, red stars of the bulge. It is the thermal signature of vast clouds of interstellar dust that have been heated to high temperatures. And the only thing that can heat dust so effectively is the intense, ultraviolet radiation pouring off massive, newborn stars. This creates a profound contradiction. From one perspective, the Sombrero's disk looks red and dead, but from another, we see a furious nursery of stellar birth, its brilliance completely veiled by the very dust that makes the galaxy so visually striking. The reason this starburst is so heavily obscured lies in the unique geometry and history of the Sombrero. That dramatic dust lane isn't a thin, decorative ribbon. It is a massive, torus-like structure brimming with gas and dust. When a galaxy is viewed perfectly edge-on, as the Sombrero is from our vantage point, this dense ring completely blocks our view of the light from newly formed stars in the optical spectrum. The brilliant blue light and pink glow of hydrogen nebulae that typically signify active star formation are utterly absorbed and scattered by the trillions of dust particles in the lane. It's like trying to see a light bulb through a thick, black blanket. The visible light is blocked, but the heat from the bulb still warms the blanket, making it glow in the infrared. This is precisely what's happening in the Sombrero. The hidden starburst is a testament to the fact that what a galaxy appears to be is often a matter of which window you use to look at it. But why is star formation so intensely concentrated in this specific region? The answer is likely a story of gravitational triggers and cosmic regulation. The immense mass of the Sombrero's central bulge and its supermassive black hole create a powerful gravitational field. This field can exert tidal forces on the gas in the inner disk, shepherding it towards specific resonant orbits, often coinciding with the location of the dust lane. Furthermore, the same past merger events that may have warped the disk and delivered fresh gas could have funneled a tremendous amount of material into this ring, creating a dense reservoir perfect for star formation. The process might be self-perpetuating. As the first massive stars form, their powerful stellar winds and eventual supernova explosions create shock waves that sweep through the surrounding gas, compressing it and triggering the collapse of even more stellar nurseries in a chain reaction. This concentrated burst of activity is what defines a starburst, even if it's a relatively short-lived phase in a galaxy's life. The fact that it's happening right under our noses, yet completely hidden in plain sight, makes it one of the Sombrero's most brilliant deceptions. This hidden furnace forces us to reconsider the galaxy's evolutionary state, suggesting that even as parts of it age gracefully, other regions are experiencing a final, dramatic flare-up of creation. Yet even as we discover evidence of violent consumption, our search of the Sombrero's neighborhood reveals an object that seems to defy the very logic of survival. Our 34th strange object is a ghost of a galaxy, a faint, sprawling smudge of light tentatively identified as an ultra-diffuse galaxy, or UDG, possibly orbiting the Sombrero at a perilously close distance. To understand why this is so bizarre, picture a galaxy the size of the Milky Way, but one that has only 1% of its stars. This is the nature of an ultra-diffuse galaxy. It is a vast cosmic cobweb, a collection of stars so thinly spread that it barely emits more light than a small globular cluster, despite covering an area thousands of times larger. Its stars are so few and far between that the galaxy is almost transparent, a mere whisper against the blackness of space. Finding such a fragile object anywhere is strange, but discovering one in the gravitational sphere of a monster like the Sombrero Galaxy is like finding a soap bubble floating intact next to an industrial fan. According to our current understanding, it simply shouldn't be there. The existence of a UDG satellite poses a direct challenge to models of galaxy formation and survival. The primary threat to a small galaxy orbiting a large one is tidal disruption. As the dwarf galaxy swings around its massive host, the difference in gravity between its near and far sides pulls it apart. For a typical, compact dwarf galaxy with a dense core, this process can take billions of years, but an ultra-diffuse galaxy, by its very nature, is the opposite of dense. It is flimsy and loosely bound, with an incredibly low stellar density. You would expect the Sombrero's immense tidal forces to shred such a wispy structure in a relatively short cosmic time, stretching its already diffuse stars into a faint, unrecognizable stream long before we could ever observe it as a coherent object. The fact that this candidate appears to be holding together suggests that our assumptions about what binds a galaxy are incomplete. So, how could this cosmic ghost possibly survive? Astronomers are exploring several compelling and strange explanations. The first and most favored theory involves the power of dark matter. While a UDG has very few stars, it might be outrageously rich in dark matter. This invisible material, which does not interact with light, provides the vast majority of a galaxy's gravitational glue. A UDG with an exceptionally massive and extended dark matter halo would be like a handful of glitter suspended in a block of clear, solid jelly. The glitter, the visible stars, are sparse, but the jelly, the dark matter, holds everything rigidly in place. This stout, dark matter-dominated core would be incredibly resilient to tidal forces, allowing the galaxy to withstand the gravitational pulling and stretching from the Sombrero that would tear a less fortified galaxy apart. In this scenario, the UDG is a cosmic fortress, its true strength hidden in its immense but invisible scaffolding. An alternative and even more exotic idea is that this candidate is not a primordial galaxy at all, but a galactic phantom, a tidal dwarf galaxy. This object might have been born from the debris of a past collision. When two gas-rich galaxies merge, the tidal forces can fling vast amounts of gas and stars out into long tails. Within these tails, the material can sometimes collapse and gravitationally bind to form new, small galaxies. These tidal dwarfs are intriguing because they are born from the recycled material of larger galaxies and are expected to contain very little dark matter, as the dark matter from the parent galaxies would not be concentrated in the tidal tails. A dark matter-free galaxy surviving near the Sombrero would be even more perplexing, as it would lack the protective halo. Its continued existence would force us to reconsider the sheer variety of ways galactic structures can form and persist. Confirming the nature of this faint smudge is incredibly difficult. It requires measuring the motions of its individual stars to determine its mass and see if it is dark matter-dominated, a monumental task at such a great distance. Whether it is a dark matter fortress or a dark matter-free phantom, its mere presence as a candidate forces a re-evaluation of the limits of galactic endurance and the hidden architecture that allows the most delicate structures in the universe to survive in the most hostile of neighborhoods. Moving deeper into the galactic nucleus, we encounter a theoretical possibility so strange it challenges our most basic assumptions about cosmic order. Our 35th object is the idea of an offset active galactic nucleus, a scenario where the supermassive black hole and its surrounding engine of activity might not be perfectly centered within the galaxy's gravitational heart. In any stable system, from a solar system to a galaxy, the most massive object is expected to reside at the dynamical center, the point around which everything else orbits. For the Sombrero, this would mean its billion solar mass black hole should sit at the precise focus of the bulge's starlight and the rotation of the entire disk. The suggestion that this gravitational anchor could be even slightly displaced is a radical proposition, pointing to a recent and violent event that literally knocked the galaxy's core out of alignment. The primary mechanism for creating such an offset is a galactic merger of a very specific kind. Imagine the Sombrero consuming a smaller galaxy that itself possessed a sizable central black hole. As the two black holes spiral toward each other, locked in a gravitational dance, they radiate energy away in the form of gravitational waves. This loss of energy causes their orbits to decay until they finally coalesce into a single, more massive black hole. However, if this merger is not perfectly symmetrical, if the two black holes have very different masses, or if they merge with a significant spin, the resulting single black hole can receive a powerful kick. This recoil, driven by the physics of gravitational wave emission, can fling the newly formed supermassive black hole out of the galactic center at speeds of thousands of kilometers per second. While not fast enough to eject it completely from the galaxy, this kick could be sufficient to displace it, sending it oscillating back and forth through the core like a clapper in a bell. We would then observe an active nucleus that is not at the exact photometric or dynamical center of the galaxy, a clear sign of a recently settled cosmic collision. An alternative and equally fascinating explanation doesn't require a kick at all, but instead posits that the offset we might detect is an illusion caused by an ongoing gravitational tug-of-war. This scenario involves a binary black hole system that has not yet merged. If the Sombrero's suspected twin nucleus is real, and it represents two separate supermassive black holes orbiting each other, then the center of mass of the system, the true dynamical center of the galaxy, would lie at a point in empty space between them. The brighter or more active of the two black holes could easily appear offset from this invisible pivot point. As the binary pair swings through its orbit, the apparent position of the AGN could even appear to wobble over time, a subtle dance that would be incredibly difficult to detect across 28 million light-years, but would provide undeniable proof of a binary system. The gravitational influence of two such massive objects so close together would create a complex and shifting gravitational field, potentially explaining other asymmetries observed in the motions of stars near the core. Detecting such a minuscule offset is at the very bleeding edge of astronomical capability. It requires exquisitely precise measurements that separate the galaxy's photometric center, the peak of its starlight, from its kinematic center, the point around which the stars are actually orbiting. Astronomers use the Hubble Space Telescope to map the distribution of starlight with phenomenal accuracy, pinpointing the brightest spot in the bulge. Then, using sophisticated spectrographs on the world's largest ground-based telescopes, they measure the velocities of thousands of individual stars in the core. By analyzing these velocities, they can calculate the galactic center of mass. If the point of maximum light and the point of maximum gravitational pull do not coincide, it would be compelling evidence for a displaced black hole. The challenge is that any offset would be vanishingly small on the sky, a difference of perhaps a fraction of a pixel in a Hubble image, and the incredible density of stars in the bulge makes untangling their individual motions a monumental task. Any hint of an offset would therefore be a landmark discovery, suggesting that the serene core of the Sombrero is still settling down from a traumatic merger that occurred in the not-too-distant cosmic past. While the death of massive stars creates spectacular supernova, the quieter, more graceful end of Sun-like stars paints the galaxy with a different kind of beauty. Our 36th, 37th, and 38th strange objects are a trio of planetary nebulae, chosen to represent the entire population of these celestial jewels scattered throughout the Sombrero. A planetary nebula has nothing to do with planets. The name is a historical accident from early astronomers who saw their round, greenish shapes and thought they resembled distant gas giants like Uranus. In reality, they are the final, fleeting breath of a star like our own Sun. After billions of years of stable life, a medium-mass star exhausts the hydrogen fuel in its core and begins to die. It swells into a red giant, becoming unstable, and then gently pulses, shedding its outer layers into space in a series of beautiful, glowing shells. The exposed, super-hot core of the star, now a white dwarf, bathes this expanding cloud of gas in intense ultraviolet radiation, causing it to fluoresce with vivid colors. Each planetary nebula is a unique work of art, a cosmic butterfly emerging from the chrysalis of a dying star, and they only shine for a few tens of thousands of years before dissipating into the interstellar medium, a mere blink in cosmic time. What makes the Sombrero's collection of planetary nebulae so scientifically valuable is that they act as a fossil record of the galaxy's star formation history. Because Sun-like stars live for so long, typically 8 to 12 billion years, the planetary nebulae we see today are the ghosts of stars that were born when the galaxy was very young. By mapping their locations and numbers, astronomers can effectively trace where and when previous generations of stars formed. For instance, if we find a large concentration of planetary nebulae in the galaxy's halo, it tells us that a significant burst of star formation occurred in that region many billions of years ago. Conversely, a relative lack of them in the outer disk might confirm that those areas have been star-poor for a very long time. In the Sombrero, this fossil record reveals a strange and telling pattern. The distribution of planetary nebulae is not smooth or uniform. They are found in surprising abundance within the massive bulge, which aligns with the idea of an ancient, rapid formation event that created that dense central hub. But their numbers in the thin disk itself are strangely sparse compared to other spiral galaxies, providing independent evidence that supports the red and dead narrative we've encountered before. The galaxy's disk has been largely infertile for eons, and the scarcity of these dying stars is the demographic proof. The strangeness deepens when we analyze the chemical composition of these glowing shells. Every planetary nebula is a time capsule, preserving the elemental makeup of the star that created it. As a star ages, it fuses hydrogen into helium in its core, and in its final giant phase, it can create heavier elements like carbon, nitrogen, and oxygen. These newly forged elements are then dredged up to the surface and expelled into the nebula. By dissecting the light from a planetary nebula, astronomers can measure the abundances of these elements. In the Sombrero, some of these nebulae show unusually strong signatures of specific elements, particularly nitrogen. This nitrogen enhancement is a significant clue. It suggests that the progenitor stars formed from gas that was already enriched with the ashes of previous, more massive stars that had lived and died in supernova explosions. This points to an environment of rapid, efficient chemical evolution in the Sombrero's past. The fact that we see this signature in nebulae within the bulge reinforces the picture of a violent, early period where star formation was frantic and self-enriching, creating a metal-rich core in a relatively short amount of time. However, other planetary nebulae, particularly those on the outskirts of the galaxy, show a much more pristine composition with lower levels of these heavy elements. This chemical dichotomy mirrors the steep metallicity gradient of the galaxy itself. but it does so using individual stars as data points, providing a much higher resolution picture of the galaxy's enrichment history. These dying stars are not just pretty lights, they are individual chemical analysts, each one reporting on the conditions of the interstellar medium from which it was born billions of years ago. Their collective testimony paints a detailed portrait of a galaxy whose different parts have lived vastly different lives, a story of cosmic segregation written in the elemental makeup of its final stellar breaths. But the influence of the Sombrero's immense dark matter halo may be far more intricate than a simple, smooth sphere of invisible mass. Our 39th strange object is perhaps the most ethereal of all, a phenomenon that isn't an object in any traditional sense but a ghostly fingerprint. It is the theoretical presence of dark matter subhalos, small, dense clumps of dark matter that are predicted to orbit within the vast expanse of the main halo like invisible islands in an invisible sea. According to our most successful cosmological model, the lambda cold dark matter paradigm, dark matter is cold, meaning its particles move slowly. This allows it to clump together gravitationally from the smallest scales upward. As a large halo like the Sombrero's forms, it does so by pulling in countless smaller clumps, which survive as distinct subhalos. We cannot see these clumps, but their subtle gravitational effects might leave faint scars on the visible structures around them, creating strange shadows that we can, in theory, detect. The primary method for hunting these shadows is a technique of extreme precision called gravitational lensing. We've already discussed how the Sombrero's total mass can lens light from distant background galaxies. But the effect of a single, small subhalo would be far more minute. Imagine a perfectly smooth lens made of glass. It would bend light in a predictable, symmetrical way. Now imagine that lens has a tiny, dense imperfection within it. As light passes near that imperfection, it would be deflected just slightly more, creating a tiny, localized distortion in the image of the background object. Astronomers search for these minute kinks and wrinkles in the faint, stretched arcs of lensed galaxies. If a background galaxy's image appears warped in a way that cannot be explained by the smooth distribution of the main halo's mass, it could be the signature of a dark matter subhalo passing in front of it, its gravity acting as a tiny, invisible lenslet within the giant lens. Detecting this effect is monumentally difficult, requiring exquisitely high-resolution images from telescopes like Hubble or James Webb, and sophisticated computer algorithms to model the gravitational field. A confirmed detection would be a direct glimpse into the clumpy, granular nature of dark matter, validating a key prediction of our fundamental model of the universe. A second powerful way to probe for these shadows is by examining the very tidal streams we discussed earlier, the stellar rivers formed from devoured dwarf galaxies. These streams are incredibly delicate structures. Their stars follow precise orbital paths dictated by the overall gravitational field of the host galaxy. If a dark matter subhalo, even a small one, passes through or near such a stream, its localized gravitational tug would perturb the orbits of the stars. This gravitational kick would create a visible gap or a wiggle in the otherwise smooth ribbon of stars, like a stone dropped into a flowing stream creating ripples and a temporary gap in the water. The presence of such gaps in the tidal streams around the Sombrero would be a smoking gun for the existence of dark matter subhalos. By studying the size and shape of the gap, astronomers could even estimate the mass of the invisible perturber. This turns the stream into a sensitive gravitational detector, a cosmic seismograph that records the passage of invisible masses through the galaxy's halo. The search for these perturbations is active, and any success would provide brilliant, indirect confirmation of the dark matter substructure that theory demands. The existence or absence of these subhalo shadows has profound implications. Finding them in the expected numbers would be a major triumph for the lambda cold dark matter model, confirming that dark matter behaves as predicted, clumping on small scales. However, a puzzling absence could point toward something even stranger. If searchers around the Sombrero and other galaxies consistently find fewer small-scale perturbations than expected, it might suggest that dark matter is not entirely cold. Perhaps dark matter particles have a small but measurable intrinsic motion, making them slightly warm. This warm dark matter would have less tendency to form the very smallest clumps, effectively erasing the fine-grained structure of the halo and leaving fewer subhalos to cast their shadows. This is known as the missing satellites problem on a smaller scale, and the Sombrero, with its complex history and extensive tidal streams, is a perfect laboratory to investigate it. These dark matter shadows are therefore a critical frontier. They are the subtle clues that could either solidify our current understanding of the universe's dominant ingredient or force us to reconsider its fundamental nature, proving that even the darkest, most elusive components of reality can betray their presence through the slightest impression on the light we can see. But the forces shaping the Sombrero are not all born from within. Some of the most powerful influences come from the vast, empty space it travels through. Our 40th strange object isn't something you can see or touch, but a relentless cosmic force known as ram pressure. Imagine the Sombrero Galaxy not as a solitary island, but as a majestic ship sailing through an invisible ocean. This ocean is the intergalactic medium, an incredibly thin but searingly hot plasma of gas that fills the enormous galaxy cluster to which the Sombrero belongs. While this gas is so diffuse it would qualify as a laboratory vacuum, the galaxy is moving through it at an astonishing speed, well over 1,000,000 miles per hour. At such velocities, even this wispy medium becomes a significant obstacle. It acts like a powerful cosmic headwind, blowing directly against the galaxy's face as it plows forward. This isn't a gentle breeze, it's a gale-force wind that can have a dramatic and stripping effect on the galaxy's own gas reservoir, the very fuel it needs for future star formation. The strange and critical factor here is the galaxy's orientation relative to this wind. Because we see the Sombrero almost perfectly edge-on, this ram pressure strikes it broadside across its entire disk. This is the worst possible angle for preserving its gas. If the galaxy were facing us, the wind would have a much smaller surface area to push against, like the sharp bow of a ship slicing through water. But in its edge-on presentation, it's like turning that ship sideways, presenting a massive sail to the storm. The hot intergalactic plasma slams into the cold, dense hydrogen gas that resides in the Sombrero's disk. The effect is a cosmic tug-of-war. The gravity of the galaxy tries to hold onto its gas while the ram pressure tries to rip it away. The outcome depends on the gas's location. In the densely packed central regions, gravity wins. The gas is too well anchored to be easily dislodged. But in the galaxy's outer disk, where the gravitational grip is weaker, the ram pressure can be triumphant. It acts like a cosmic pressure washer, efficiently scouring the tenuous outer gas and blowing it out into the galaxy's wake, leaving behind a trail of lost potential. This process has a direct and observable consequence. It actively contributes to the Sombrero's red and dead character, particularly in its outer realms. The galaxy is effectively being stripped of the raw materials needed to make new stars. By removing the cold hydrogen gas from the outer disk, ram pressure strangles future star formation in those regions. It's a form of galactic quenching that originates from outside the galaxy itself, a stark contrast to the internal quenching that might be caused by the central black hole. This could explain why the star formation in the Sombrero seems so concentrated and why the outer disk appears so quiescent. The galaxy is fighting a constant battle against its environment, losing its gaseous fuel to the relentless headwind of intergalactic space. The presence of high-velocity gas clouds flowing out of the galaxy, which we discussed earlier, could very well be the direct result of this ongoing ram pressure stripping, the visible evidence of gas being blown away by this cosmic gale. What makes this interaction particularly fascinating is that it is not a one-time event but a continuous process. As long as the Sombrero continues its high-speed journey through the galaxy cluster, it will experience this pressure. This means the galaxy we see today is a snapshot of an ongoing transformation. Its current size, shape, and gas content are all influenced by this eternal wind. The iconic dust lane itself might owe its sharp, well-defined appearance to this process. The ram pressure could be compressing the gas along the leading edge of the disk, enhancing the contrast between the dusty lane and the bright bulge. Furthermore, this external pressure might work in concert with the galaxy's internal dynamics. The ram pressure could be helping to maintain the warped shape of the disk by constantly pushing against it, or it could even be influencing the flow of the counter-rotating gas cloud, adding an extra layer of complexity to its eventual fate. The Sombrero Galaxy, therefore, is not an isolated system evolving in a vacuum. It is in a dynamic dance with its environment, its structure and future being sculpted as much by the invisible ocean it sails through as by the violent history written in its stars. As we peer even closer into the galaxy's brilliant core, past the potential offset of the black hole and the frenetic motions of stars, we encounter a structural oddity that challenges our very perception of galactic stability. Our 41st strange object is the theoretical existence of a tilted inner disk. This isn't about the warped outer dust lane we discussed earlier. This is a suggestion that the very heart of the Sombrero, the blazing bulge of stars we see as a unified sphere, might actually be a separate, dense, and rapidly spinning disk of stars that is cocked at an angle relative to the main galactic disk. Imagine a galaxy within a galaxy, a brilliant miniature merry-go-round of stars spinning merrily along inside the larger carousel, but on a completely different axis. This nested, misaligned system would make the Sombrero's core a dynamically bizarre and volatile place, a celestial gyroscope within a gyroscope. The formation of such a structure is a story of galactic indigestion on a grand scale. It almost certainly points to a major accretion event, but not just any merger. For a tilted inner disk to form and persist, the Sombrero would have needed to consume a smaller, gas-rich galaxy that arrived on a very specific inclined orbit. As this victim galaxy was torn apart by tidal forces, its gas possessing its own angular momentum would not have simply settled into the existing plane of the Sombrero's disk. Instead, this fresh supply of material would have retained the orbital memory of its original path, cascading down toward the core but settling into a new, separate disk that rotates around a different axis. This is a process known as polar accretion. Over time, this newly delivered gas would have fueled an intense burst of star formation, creating a new generation of stars that all inherited the unique orbital plane of the incoming material. The result is a bright, distinct stellar disk nested inside the main one, a permanent fossil of that ancient cosmic meal whose spin direction is fundamentally askew. The dynamical challenges presented by such a configuration are immense. A stable galaxy thrives on equilibrium. Its stars and gas orbit in a calm, orderly fashion within a single, dominant plane. Introducing a second, misaligned disk within this system is like dropping a spinning top inside another spinning top. The gravitational pull between the two disks creates a constant, nagging torque. The larger outer disk tries to pull the inner disk into alignment, while the inner disk, with its own significant mass and angular momentum, stubbornly resists. This gravitational struggle induces a phenomenon called precession, where the axis of the inner disk slowly wobbles like a child's top slowing down. This isn't a fast process. It unfolds over hundreds of millions of years, but it constantly churns the gravitational environment of the core. This turmoil can have profound effects, funneling gas flows into chaotic paths, potentially triggering unusual star formation patterns, and even influencing the feeding habits of the central supermassive black hole by periodically directing streams of fuel toward it from unexpected angles. The presence of a tilted inner disk turns the galactic core from a serene retirement home for old stars into a dynamic and unsettled engine room. Evidence for this strange nested structure is subtle and comes from detailed kinematic maps of the stars in the bulge. By measuring the velocities of thousands of individual stars, astronomers can detect distinct groups moving with different patterns. If the bulge were a simple, puffed-up sphere of stars, their motions would be largely random. However, if a significant fraction of these stars are part of a rapidly rotating disk, their velocities will show a clear, organized flow. In the Sombrero, studies have indeed revealed a population of stars in the inner regions moving with a coherent rotation that is slightly misaligned with the main disk. This is the tantalizing signature of the tilted inner disk. Its existence would beautifully tie together several of the galaxy's other mysteries. It could be the driving force behind the warped outer disk, as the gravitational influence of the misaligned inner structure torques the larger one. It could also help explain the galaxy's complex metallicity gradient, as the stars in this inner disk would have formed from gas with a different chemical history than the stars in the main disk. This single idea, a spinning disk tilted within a disk, paints a picture of a galaxy that is not a monolithic entity but a complex archaeological site, built in layers through a history of violent and precise mergers. While the serene glow of starlight defines the Sombrero's beauty, the potential for a cataclysm of pure energy, invisible to our eyes, adds a layer of dramatic tension to our exploration. Our 42nd strange object is not something we have seen, but something that could theoretically happen at any moment, a candidate for a fleeting, colossal gamma-ray flash. Gamma rays represent the most energetic form of light in the universe, packing billions of times more energy per photon than visible light. They are the signature of the most extreme physical processes imaginable. The idea that such an event could originate from the seemingly placid Sombrero Galaxy transforms it from a static portrait into a potential cosmic powder keg, waiting for a trigger we cannot predict. One of the most plausible sources for such a flash lies dormant at the galaxy's very heart. We already know the Sombrero hosts a supermassive black hole of staggering mass, currently in a quiet state. However, this quiescence might be temporary. If a significant amount of gas like that from the counter-rotating cloud we discussed were to suddenly spiral inward, it could temporarily awaken this sleeping giant. In such a scenario, the black hole could transition into a specific type of active galactic nucleus known as a blazar. This occurs when one of the black hole's powerful relativistic jets is pointed almost directly at Earth. From our vantage point, the emission from that jet, which includes incredibly energetic gamma rays, would be massively amplified, like staring directly into the beam of a cosmic lighthouse. The Sombrero would, for a brief period, become one of the brightest gamma-ray sources in the sky, a brilliant flash that could last for hours, days, or even weeks before fading back into obscurity. Detecting such an event would be a monumental discovery, providing a real-time view of the black hole's feeding mechanics and the physics of its jets, all from a safe distance of 28 million light-years. An alternative and even more violent source of a gamma-ray flash has nothing to do with the central black hole. It could originate from the collision of two ultra-dense stellar corpses, neutron stars. When these remnants of supernova explosions, each just a dozen miles across but more massive than our Sun, spiral into each other, they create one of the universe's most energetic explosions, a short gamma-ray burst. In a fraction of a second, such an event can release more energy than our Sun will emit in its entire 10 billion-year lifetime, all focused into a narrow beam of gamma radiation. The Sombrero Galaxy, with its vast population of stars and history of stellar formation, undoubtedly contains countless neutron stars. The dense environments of its globular clusters would be especially favorable for the complex gravitational dances that can bring these objects together. If a pair were to merge and the resulting jet were oriented toward us, we would witness a sudden, blinding spike of gamma rays, a literal blink and you'll miss it event that would signal the catastrophic birth of a black hole and the creation of heavy elements like gold and platinum, forged in the unimaginable furnace of the collision. The true strangeness of this candidate event lies in its profound unpredictability. Unlike the steady rotation of stars or the slow warp of the dust lane, a gamma ray burst is transient. It is a singular, unrepeatable moment of cosmic violence. Our telescopes would have to be looking in exactly the right place at exactly the right time to catch it. This element of chance makes the Sombrero a permanent subject of interest for satellites like NASA's Fermi Gamma Ray Space Telescope, which constantly scans the sky for such fleeting outbursts. The absence of a detection so far is not proof that such events don't occur. It simply means we haven't been lucky yet. This possibility reminds us that our view of the cosmos is a snapshot, and that the peaceful galaxy we study today could tomorrow reveal a completely different, ferociously energetic face. The potential for a gamma-ray flash underscores the dynamic and unfinished nature of the Sombrero's story, where the most dramatic chapters may be written in a blinding instant of light that has yet to reach our telescopes. While the lopsided stellar halo and the faint tidal streamers tell a story of galactic cannibalism, one particular river of stars could hold the key to the very first chapter of the Sombrero's existence. Our 43rd strange object is the theorized metal-poor stellar stream, a faint, arching filament of stars within the halo that would stand out for its profound chemical purity. To understand why this is so significant, we need to think about cosmic chemistry. The early universe, just after the Big Bang, contained only the simplest elements: hydrogen, helium, and a trace of lithium. Everything else, the carbon in our bodies, the oxygen we breathe, the iron in our blood, was forged later, in the nuclear furnaces of stars and scattered across space when those stars died in supernova explosions. Therefore, a star's metallicity, its abundance of these heavier elements, acts as a cosmic clock. Stars with very low metal content must have formed from pristine gas early in the universe's history, before many supernovae had a chance to pollute the interstellar medium. Finding a concentrated stream of such stars would be like discovering a living population of dinosaurs. They are ancient relics among the oldest objects in the entire cosmos. This stream would be a direct fossil from the cosmic dark ages, a preserved piece of one of the very first proto-galaxies that ever formed. The prevailing model of galaxy formation, known as hierarchical clustering, suggests that giant galaxies like the Sombrero were not born whole. Instead, they were built over billions of years through the assembly of countless smaller building blocks, the earliest, smallest galaxies that condensed from the primordial gas. These pioneer galaxies were composed of this pristine material, and their stars would have been extremely metal-poor. When the Sombrero consumed one of these ancient building blocks, it would have torn it apart, scattering its stars into the halo. But if the accretion event happened in a very specific way, the stars could have remained gravitationally bound to each other along their original orbital path, forming a coherent stream that has persisted to this day. This stream would therefore be more than just evidence of a past meal. It would be a preserved sample of a first-generation galaxy, a time capsule from an era when the universe was less than 1 billion years old. Its stars would be the galactic equivalent of archaeologists uncovering a perfectly preserved ancient city, offering an unobstructed view into the conditions of the early universe. The scientific value of confirming such a stream would be immeasurable. By studying the precise orbital path of these ancient stars, astronomers could rewind the clock with incredible accuracy, tracing their path back to the exact location and manner of that first foundational merger. This would tell us about the initial conditions from which the Sombrero began its growth. Even more importantly, analyzing the light from these stars would allow us to perform stellar archaeology on a grand scale. Their spectra would reveal the exact chemical composition of the primordial gas from which they formed. any tiny deviations from the expected ratios of hydrogen and helium could provide critical clues about the physics of the Big Bang itself and the nature of the first moments of creation. Furthermore, the internal dynamics of the stream, how the stars move relative to one another, could be used to probe the distribution of dark matter within that original proto-galaxy, giving us a unique window into how dark matter structured the universe from its very beginning. This single, faint stream would connect the majestic galaxy we see today directly to the oldest events in cosmic history, making it one of the most profound archaeological sites imaginable. And so we return to the very heart of the matter, to the brilliant core of the Sombrero Galaxy and the enduring mystery of its twin nucleus. While the possibility of a distorted stellar disk offers one explanation, the more tantalizing scenario is that we are witnessing something far more dynamic, a binary supermassive black hole system. Imagine not one but two gravitational titans, each with the mass of hundreds of millions of suns, locked in a slow cosmic dance at the galaxy's center. This isn't just a theoretical curiosity. If confirmed, it would be the ultimate evidence of the Sombrero's violent past, a smoking gun proving a major galactic merger. The dynamics of such a system are mind-bending. These black holes would be orbiting a common center of gravity, a point in empty space between them. Their orbital dance would not be a swift waltz. Given their immense mass and separation, a single orbit could take thousands of years to complete. As they spiral around each other, their overwhelming gravity would churn the surrounding star field, whipping nearby stars to incredible speeds and flinging others out of the galaxy entirely as hypervelocity runaways. This gravitational turmoil could be the very engine behind the strange velocity dispersions we observe in the core, creating a region of chaotic stellar motion that is anything but the serene retirement home it appears to be from a distance. One of the most profound consequences of this binary dance would be the emission of gravitational waves. As predicted by Einstein's theory of general relativity, any massive object undergoing acceleration ripples the very fabric of spacetime itself. A binary black hole system is a perfect generator of these ripples, constantly losing energy as gravitational radiation. This energy loss causes their orbits to slowly decay, drawing them closer together over hundreds of millions of years. While the waves from the Sombrero's system would be too faint for our current detectors like LIGO to hear, their existence is a key prediction of our understanding of gravity. Their eventual fate is a cataclysmic merger, an event that would unleash a titanic burst of gravitational waves shaking the cosmos. But long before that final union, their interaction could create strange and observable phenomena, particularly regarding the galaxy's active galactic nucleus or AN activity. The presence of a second supermassive black hole could explain the central paradox of the Sombrero's core, a billion solar mass engine that is strangely quiet. The gravitational influence of a binary partner can disrupt the smooth flow of gas needed to fuel a bright accretion disk. Instead of falling neatly onto a single black hole, gas clouds could be torn apart, diverted, or caught in a gravitational tug of war between the two monsters, preventing either from establishing a stable, well-fed disk that would shine as a brilliant quasar. The AGN activity we do see, the faint, sputtering jets, might be the result of sporadic, chaotic feeding events, brief moments when a clump of gas momentarily escapes the chaotic dynamics and falls onto one of the black holes. This could lead to another bizarre possibility, periodic activity. As the black holes orbit, their gravitational focus shifts. There might be phases in their multi-millennial orbit where their combined gravity efficiently funnels gas toward them, leading to a temporary brightening of the AGN. Then, as they move to a different orbital configuration, that fuel supply could be cut off and the core would fade back into quiescence. We could be seeing the Sombrero's core in a quiet phase of this incredibly long cycle. Furthermore, if one black hole has a more active accretion disk than the other, its brilliance could periodically be eclipsed by the dust and gas swirling around its companion as they orbit, creating a slow, regular dimming in certain wavelengths of light. Detecting such a cycle would be incredibly difficult given the timescales involved, but it would be a hallmark signature of a binary system. The potential for a binary black hole at the heart of the sombrero transforms this beautiful static image into a scene of slow-motion gravitational drama. It is a system evolving on a timescale we can barely comprehend, a dance of darkness whose final, merging step will redefine the galaxy's core for eons to come. Now, as we catalogue the known and the theorized, we must confront an object that defies all our existing labels, a point of light within the sombrero that behaves like nothing else we've ever seen. Our 45th strange object is simply known as an unidentified variable, a celestial rebel that flickers and flares with a stubborn refusal to follow any recognizable pattern. This isn't the rhythmic pulse of a Cepheid variable star or the predictable outburst of a feeding black hole. This is chaos incarnate, an object that brightens and fades at random intervals, sometimes over days, other times over months, with shifts in color that suggest its very nature is in flux. In a universe governed by physical laws, where we pride ourselves on classifying and modeling every kind of celestial behavior, this mystery object is a profound and humbling reminder of how much we have yet to learn. It sits in our data, a persistent anomaly that has resisted every attempt to squeeze it into a known category, representing the thrilling and sometimes frustrating frontier of discovery. The challenge in understanding this object lies in the very nature of its variability. When astronomers study a changing star or a flickering black hole, they look for patterns. A pulsating variable star has a clear period luminosity relationship. Its changes are as reliable as clockwork. The flickering of an X-ray binary follows certain rules tied to the rate of mass transfer from a companion star. Even the chaotic outbursts of a flaring black hole have certain spectral signatures, telltale emissions in specific wavelengths of light that betray the extreme physics at work. The unidentified variable in the sombrero possesses none of these hallmarks. Its light curve, the graph of its brightness over time, is a jagged, unpredictable mess. It might remain steady for a year, then suddenly double in brightness over a week, only to drop back down just as rapidly with no repeating cycle. Even more baffling are its color changes. An object typically gets bluer as it gets hotter and brighter, and redder as it cools and dims. This object, however, has been observed to sometimes brighten while becoming redder, a combination that contradicts the basic behavior of most stellar and accretion processes. It's as if we're watching several different kinds of astrophysical events happening to a single source all at once. So, what could possibly be causing this bizarre behavior? Astronomers are forced to consider possibilities that range from the exotic to the truly revolutionary. One compelling idea is that we are not looking at a single object, but a chance alignment of two or more independent variable sources along our line of sight. Imagine a faint, irregularly variable star in the foreground of the sombrero, positioned directly in front of a flickering X-ray binary within the galaxy itself. The combined light from these two unrelated objects could create a complex, unpredictable pattern that is simply an illusion of perspective. While possible, meticulous analysis of the object's position makes this alignment statistically unlikely, pushing scientists to seek a more unified explanation. A more exciting possibility is that we are witnessing a new, unknown type of cataclysmic variable star. This could involve a white dwarf in a binary system that is accreting material from its companion in an extraordinarily unstable way. Perhaps the accretion disk around the white dwarf is prone to massive, irregular instabilities, giant magnetic storms, or avalanches of material that crash onto the star's surface in unpredictable bursts. Alternatively, the object could be a microquasar, a stellar mass black hole feeding from a companion, but one that is behaving in a way we've never documented. Its accretion disk might be precessing or wobbling, causing its jet to point toward us only at irregular intervals, creating the observed random flaring. Perhaps the most thrilling hypothesis is that this object represents a completely new class of astrophysical phenomenon. It could be the signature of an immense stellar merger that occurred recently in cosmic terms, and we are now seeing the complex and chaotic aftermath as the merged object settles into a new, stable form. Or it could be something even more esoteric, like the activity of an intermediate mass black hole that is feeding in a peculiarly inefficient and erratic manner, a feeding style we have no existing model for. The very existence of this unclassifiable object is a powerful message. It tells us that our catalogs of cosmic variables are not complete, that the universe still holds surprises that can force us to rewrite our textbooks. Every unpredictable flicker from this distant point of light is a challenge, a direct call to develop new theories and new observing strategies to finally understand what is happening in the dark corners of a galaxy we thought we knew. But our journey into the Sombrero's strangest phenomena now takes us beyond the familiar confines of its stars and dust, out into the vast, almost empty space of its extended halo. Our 46th strange object is a ghost of a different kind, a theoretical possibility that stretches our imagination of where cosmic violence can occur. It is the concept of an intergalactic supernova remnant. We are accustomed to thinking of supernova as events that happen within the dense stellar cities of a galactic disk, their glowing debris confined by the surrounding interstellar medium. But imagine a supernova explosion detonating in the profound isolation of intergalactic space, far from any significant concentration of stars. The remnant from such an event would be a bizarre and lonely object, an expanding bubble of hot, metal-enriched gas floating in near-total emptiness, a solitary monument to a star that died alone. How could a star find itself in such a desolate place to meet its end? The most likely scenario involves the same gravitational drama we've seen throughout the Sombrero's history. When a dwarf galaxy is torn apart by tidal forces, it doesn't just lose its stars, it also loses the stars that were once gravitationally bound within its globular clusters. These clusters can be ejected, flung out into the halo as the dwarf galaxy is shredded. Inside one of these exiled clusters, a massive star could reach the end of its life. Alternatively, the explosion could be the final act of a hypervelocity runaway star, one of those stellar projectiles flung from the galactic center at such speed that it achieved escape velocity. This star would have spent millions of years traveling through the halo, a lonely voyager, until its fuel ran out and it collapsed in a spectacular supernova blast, with no other stars for light years around to witness its demise. The remnant of this explosion would therefore be a direct consequence of the galaxy's gravitational violence, a cosmic splatter pattern marking the final resting place of an exile. The physical nature of this remnant will be profoundly different from its galactic cousins. A supernova remnant inside a galaxy expands into a relatively dense medium, slamming into other gas clouds, creating bright, sharp shock fronts and slowing down relatively quickly. But a remnant expanding into the virtual vacuum of the intergalactic medium would meet almost no resistance. It would expand rapidly and freely, cooling much more quickly and remaining extremely faint and diffuse. Instead of a classic, intricate nebula like the Crab, it would more closely resemble a vast, faint, and perfectly spherical bubble. Detecting such an object would be an immense challenge. It would emit most of its energy in very low-frequency radio waves and in extremely soft X-rays, signatures that are easily lost against the background glow of the universe. Confirming its existence would require painstaking observations to distinguish its subtle emission from the general haze of the galactic halo, a task akin to spotting a single, faint soap bubble against a complex backdrop. Yet, if found, this lonely bubble would be a scientific treasure trove. Its isolation would make it a perfect natural laboratory, Without the complicating factors of a dense surrounding environment, astronomers could study the pristine physics of a supernova shockwave as it expands into a near-perfect vacuum. They could measure how the elements forged in the stellar explosion, oxygen, silicon, iron, mix and dissipate in the simplest possible conditions. This would provide unparalleled data for models of supernova nucleosynthesis and dynamics. Furthermore, the mere existence of such a remnant would act as a direct probe of the conditions in the galactic halo. By measuring the size and expansion rate of the bubble, scientists could estimate the density of the incredibly thin gas in that region, a measurement that is otherwise nearly impossible to obtain. This intergalactic supernova remnant would be more than just a curiosity. It would be a unique instrument for measuring the invisible and understanding the final journeys of stars cast out from their galactic homes. But beyond the light we can see and the specific cataclysms we might witness, the Sombrero Galaxy contributes to the cosmos in a far more subtle and universal way, through a vibration that resonates through the very fabric of space and time itself. Our 47th strange object is perhaps the most abstract yet, because it isn't something you can point a telescope at. It is the galaxy's contribution to the gravitational wave background, a faint, persistent hum that fills the entire universe. To understand this, we need to shift our perspective from observing the galaxy to, in a sense, listening to it. Gravitational waves are ripples in space-time, predicted by Einstein, that are created when massive objects accelerate. The most dramatic sources are the collisions of black holes and neutron stars, which send out powerful, short-lived chirps that our detectors like LIGO and Virgo can now pick up. But imagine the combined effect of millions of less dramatic events. Throughout the Sombrero, countless binary systems are constantly orbiting, pairs of stellar mass black holes, duos of neutron stars, even binary white dwarfs. Each of these pairs, as they spiral around each other, emits an incredibly faint whisper of gravitational waves. Individually, these whispers are far too quiet to ever be detected from 28 million light-years away. But collectively, they create a steady, overlapping signal, a cosmic chorus of gravitational noise. This is the stochastic gravitational wave background, and the Sombrero Galaxy, with its vast population of stars and compact objects, is one of countless contributors to this universal hum. This represents a completely new way of observing a galaxy. For centuries, our knowledge has come from photons, particles of light across the electromagnetic spectrum. Now we are developing the ability to sense the universe through the direct distortion of spacetime itself. The Sombrero's contribution to this background is like a single instrument in a vast cosmic orchestra. We cannot yet pick out its individual note from the cacophony of all the galaxies in the universe, but we know it's there, adding its unique timbre to the overall sound. This hum is the integrated sound of the galaxy's dynamical history. The strength and frequency of the signal depend on the number and types of binary systems within it. A galaxy with a recent history of vigorous star formation, like the Sombrero's past starbursts, will have produced more massive stars that ended their lives as black holes and neutron stars. Many of these will be locked in binary systems, constantly emitting gravitational waves as they orbit. Therefore, the Sombrero's specific signature in the gravitational wave background is a direct reflection of its stellar life cycle and its population of dead stars. By one day being able to analyze this background in fine detail, we could potentially estimate the total number of these binary remnants within the galaxy without ever seeing a single one directly, using gravity itself as our census tool. The implications of detecting this background are profound for understanding the Sombrero's future. Every binary system emitting gravitational waves is slowly losing orbital energy. This energy loss causes the objects to spiral closer together over billions of years. For some, this leads to an eventual merger, a spectacular event that would create a louder chirp in the gravitational wave spectrum. The persistent hum of the background is therefore the sound of countless futures being sealed. It is the noise of orbital decay on a galactic scale. The Sombrero's hum is the sound of its stellar populations gradually winding down, of binary stars destined for collision. This provides a long-term forecast for the galaxy. A louder contribution at certain frequencies might suggest a higher population of close binary black holes, hinting at a future filled with more frequent merger events. This gravitational wave background is not a static picture. It's a dynamic projection of the galaxy's evolutionary fate, a slow-motion soundtrack to its ongoing transformation. While we currently listen to the combined hum of the entire universe, future generations of space-based gravitational wave observatories, like the proposed LISA mission, may have the sensitivity to begin distinguishing the contributions from nearby massive galaxies. When that day comes, we will be able to tune our instruments to the specific frequency of the Sombrero, listening to the quiet, persistent vibration of its hidden binary heart, and understanding the galaxy not just by its light but by its gravity. As we unravel the cosmic tapestry of the Sombrero Galaxy, we arrive at perhaps the most elusive and speculative possibility of all, an encounter with an entity that is fundamentally invisible. Our 48th strange object is not just difficult to see. By its very nature, it might be impossible to observe directly. It is the theoretical dark galaxy, a vast, coherent structure made almost entirely of dark matter, containing little to no stars or gas to betray its presence with light. The idea that such a phantom could be responsible for some of the Sombrero's most persistent mysteries forces us to reconsider the very nature of cosmic interactions and the limits of our perception. The concept of a dark galaxy emerges naturally from our leading model of the universe, lambda cold dark matter. This theory predicts that dark matter, which outweighs visible matter by a factor of 5 to 1, should clump together gravitationally across all scales. Just as visible matter coalesces into galaxies of stars, dark matter should form halos and subhalos of its own. In many cases, these dark matter clumps would have acted as the gravitational seeds for the formation of the luminous galaxies we see. But what if, in some instances, a large clump of dark matter failed to attract a significant amount of baryonic matter, the ordinary atoms that make up stars and gas? The result would be a dark galaxy, a massive object possessing a gravitational field as strong as a small visible galaxy, but floating through space as a ghostly, unseen presence. Now, imagine such a dark galaxy passing relatively close to the Sombrero on a long, looping orbit. Its gravitational influence would be profound. Without the friction and drag that occurs when two gas-rich galaxies collide, the interaction would be a purely gravitational affair, a ghostly tug-of-war. The dark galaxy's pull would warp the delicate disk of the Sombrero, much like an invisible hand pressing on a spinning vinyl record. This could provide an elegant explanation for the pronounced S-shaped warp we observe in the galaxy's iconic dust lane. A close flyby from a massive, dark object could induce precisely the kind of large-scale, coherent distortion that has been so difficult to explain through other means. Similarly, the vast, lopsided stellar halo could be the result of this phantom's gravitational influence stirring up the outer reaches of the galaxy over billions of years, pulling the distribution of stars into an asymmetric shape without the messy aftermath of a stellar collision. This idea becomes even more compelling when we consider the mystery of the missing dwarf satellites. Our telescopes have found far fewer small, visible companion galaxies around the Sombrero than our models predict. But what if the majority of its companions are not failed, star-poor dwarfs, but completely dark galaxies? The Sombrero's gravitational neighborhood could be teeming with these invisible entities, their presence only hinted at by the gravitational disturbances they impose on their brilliant, luminous host. The faint tidal streams we see could be the result of the dark galaxy's gravity perturbing the orbits of stars already within the Sombrero's halo, rather than solely from the disruption of visible dwarf galaxies. It would mean that the history of the Sombrero is not just written in the stars it has consumed, but also in the unseen battles it has fought with ghosts. Proving the existence of such an interaction is one of the greatest challenges in modern astronomy. How do you find something that emits no light? The primary method relies on the same technique used to infer dark matter itself, its gravitational effects. Astronomers would construct exquisitely detailed models of the Sombrero's mass distribution based on the motions of its stars and the shape of its gravitational lensing signature. They would then see if a perfectly smooth, symmetric dark matter halo can account for all the observed perturbations, the warp, the lopsided halo, the peculiar motions of outer stars. If the models consistently fail unless they include the gravitational pull of a nearby, massive, and invisible perturber, that would be the strongest possible evidence for a dark galaxy. It would be a case of celestial deduction where the culprit is identified not by being seen, but by the unmistakable imprint it leaves on the scene. The implications of confirming such an entity would be staggering. It would provide direct evidence for the existence of dark matter structures that formed but never ignited with starlight, offering profound insights into the conditions of the early universe. It would suggest that the cosmic web is even more rich and complex than we thought, woven with both threads of light and threads of pure darkness. For the Sombrero Galaxy, it would mean that its serene beauty is not just a mask for a violent history of stellar collisions, but also for a more subtle, ongoing dance with an invisible partner, a dance where gravity alone choreographs the steps, and the only evidence is a slight, persistent tilt in a cosmic hat. But beyond the ghostly pull of a potential dark galaxy lies an even more exotic possibility, one that reaches back to the very first moments of creation. Our 49th strange object is not a single entity but a hypothetical population of ancient relics that could be hiding in plain sight, woven throughout the Sombrero's immense dark matter halo. This is the idea of a primordial black hole swarm. These wouldn't be the black holes we know, formed from the collapsing cores of dead stars. Primordial black holes are thought to be a product of the infant universe, born not from stellar death but from the violent birth pangs of the cosmos itself. In the incredibly dense and hot conditions just fractions of a second after the Big Bang, random fluctuations in density could have been so extreme that pockets of space-time collapsed directly into black holes. These primordial objects could span a vast range of sizes, from as small as an asteroid to many times the mass of our Sun. If they exist in significant numbers, they could account for a portion, or even all, of the mysterious dark matter that holds the Sombrero together. The gravitational signature of such a swarm would be subtle yet pervasive. Unlike a smooth, cloud-like distribution of dark matter particles, a halo made of discrete black holes would have a granular texture. Its gravity wouldn't be perfectly even. Imagine the difference between a perfectly smooth slope and a slope covered in gravel. You could still slide down both, but the journey would be much bumpier on the gravel. For the Sombrero, this granularity could manifest in delicate ways. The orbits of the faintest, most distant stars in the halo might exhibit tiny, unexplained wiggles as they are gently tugged by the unseen black holes they pass near. The fine, filamentary structures of tidal streams could develop faint kinks or gaps if a particularly massive primordial black hole plowed through them. Even the gravitational lensing effects we've discussed could be affected. The light from a distant background galaxy might be minutely distorted in a speckled pattern as it passes through the swarm, rather than being bent by a perfectly smooth gravitational field. Detecting these effects is currently beyond our reach, but it represents a future frontier where we could indirectly sense the lumpy architecture of the dark matter halo. The implications of this idea are staggering, connecting the Sombrero Galaxy directly to the most extreme physics of the Big Bang. If a significant fraction of its dark matter is indeed tied up in these primordial black holes, then the galaxy is not just a collection of stars, it is also a museum of cosmic artifacts displaying preserved remnants from the universe's first second. This would solve two profound puzzles at once: the nature of dark matter and the origin of some black holes. It could provide an elegant explanation for the existence of supermassive black holes in very early galaxies. They wouldn't have needed to grow from stellar remnants, but could have started as large primordial seeds around which the first galaxies then assembled. The Sombrero's own billion solar mass central black hole could have such an origin, a primordial giant that has been anchoring the galaxy since its inception. Of course, this remains a highly speculative theory. Observational constraints, particularly from experiments that monitor the gravitational microlensing of stars in other galaxies, have largely ruled out primordial black holes in certain mass ranges from making up all of dark matter. But windows of possibility remain, especially for black holes of intermediate mass or those in the asteroid mass range. The Sombrero Galaxy, with its complex dynamics and immense dark matter halo, serves as a perfect cosmic laboratory to test these ideas. Future observations that map the galaxy's gravitational field with exquisitely high precision may one day reveal the telltale bumps and wrinkles that would betray the presence of this ancient swarm. Until then, the idea stands as a testament to the depth of the unknown, a reminder that the darkness holding the sombrero together might not be a uniform mist, but a glittering, invisible archipelago of cosmic fossils, each one a silent witness to the universe's explosive beginning. And so we arrive at our final and perhaps most profound strange object, one that is not an object in any traditional sense, but a ghostly signature, a potential whisper of creation and destruction happening in the absolute darkness of the galaxy's heart. This 50th and final enigma is the Sombrero Galaxy's candidacy as a great annihilator, a place where the universe's most elusive component might be revealing its identity through a spectacular act of self-annihilation. The target of this search is dark matter, and the hypothesis is as elegant as it is revolutionary. What if the particles that make up this mysterious substance are their own antimatter counterparts? Theoretical models suggest that certain proposed dark matter particles, known as weakly interacting massive particles or WIMP, could be what scientists call Majorana particles. This means a WIMP could be its own antiparticle. If this is true, then whenever two WIMP collide under the right conditions, they would annihilate each other in a flash of pure energy, converting their entire mass into other particles, most notably a cascade that includes high-energy gamma-ray photons. The core of the Sombrero Galaxy presents the perfect hunting ground for this phenomenon. Annihilation requires density. The more densely dark matter is packed, the greater the chance these rare collisions will occur. And the heart of the Sombrero, dominated by that immense billion solar mass black hole and its incredibly dense stellar bulge, is thought to be anchored by an equally immense and concentrated halo of dark matter. The gravitational pull of all that visible matter would have drawn the dark matter into an even denser cloud, creating a region where the particle traffic jam would be at its most intense. If WIMP are real and they behave as predicted, then the galactic center should be shining with a faint but distinct gamma-ray glow, the final, fiery signature of dark matter particles meeting their end. Detecting this specific gamma-ray signature would be the smoking gun, the first direct evidence of what dark matter actually is. It would transform our understanding of the universe from its largest scales down to its most fundamental particles. The challenge, of course, is monumental. The galactic center is a naturally violent place, teeming with other potential sources of gamma rays, from pulsars and microquasars to the diffuse emission from cosmic rays interacting with gas clouds. The signal from dark matter annihilation would be subtle, a smooth and extended excess of gamma rays concentrated around the core, with a specific energy spectrum that depends on the mass of the WIMP particle. Astronomers using instruments like the Fermi Gamma Ray Space Telescope have spent years meticulously scanning the Sombrero and other similar galaxies. carefully subtracting all the known astrophysical backgrounds, searching for that telltale residual glow that cannot be explained by anything else. The search is a delicate balancing act. Too much other activity can drown out the signal, but a galaxy that is too quiet might not have a dense enough dark matter core to produce a detectable signal. The Sombrero, with its powerful core and relative quiescence in other high-energy processes, sits in a promising sweet spot. This search connects the fate of the Sombrero Galaxy to the most fundamental questions in physics. Confirming it as a great annihilator would not only solve the 85-year-old mystery of dark matter, but could also provide clues to physics beyond the standard model, pointing toward a more complete theory of the universe. It would mean that the serene beauty of the Sombrero's silhouette is more than just a mask for a violent history of stellar collisions and gravitational turmoil. It is also a screen onto which the invisible majority of the cosmos is projecting a faint, flickering image of its own fundamental nature. Every strange object we have encountered on this journey, from the quiet black hole and the warped disk to the orphan star clusters and the high-velocity gas, has been a piece of a puzzle. This final piece, the search for the gamma-ray glow of annihilation, is the one that could tie them all together, revealing that the dark matter that shapes the galaxy's vast structure is also, in its final moments, capable of creating a light that illuminates the deepest secrets of the universe. And so, after this incredible journey through 50 strange objects, what are we left with? We began at the very heart of darkness with a billion solar mass black hole that defies expectation by its profound silence. We then discovered that this heart might not be alone, with the tantalizing possibility of a twin nucleus suggesting a violent merger frozen in time. We saw how the galaxy's beautiful facade is subtly distorted by a warped dust lane, a wobble that whispers of ancient gravitational encounters, and we peered into the invisible realm, finding evidence for a dark matter halo so massive it dictates the very rotation of the stars. We explored a glittering swarm of nearly 2,000 globular clusters, a population 10 times larger than our own Milky Ways, each cluster a trophy from a past cosmic feast. We witnessed the dynamic breath of the galaxy in high-velocity gas clouds, some falling into fuel future generations, others being violently expelled. We encountered the bizarre ultraluminous X-ray sources, enigmatic objects that could be intermediate mass black holes or stellar corpses feeding in impossible ways, and we pondered the profound emptiness around the galaxy, a missing satellite problem that challenges our deepest cosmological models. We traced the scars of this violent history in a lopsided stellar halo and the ghostly arcs of tidal streamers, the final orbits of devoured dwarf galaxies. We considered the mind-bending possibility of a polar ring, a structure that would seal the case for a catastrophic collision, and we uncovered a startling chemical discontinuity in the stars themselves, a steep metallicity gradient that points to a hybrid origin. We grappled with the paradox of a galaxy that looks like a spiral but acts like an elderly elliptical, with vast red and dead regions where star formation has been quenched. We hunted for hypervelocity runaway stars, stellar projectiles flung from the galactic core, and we found the fading echoes of spiral arms in fossil structures that speak of a more active past. We investigated flickering compact objects, the chaotic remains of dead stars, and we searched for the faint mirage of a gravitational lensing arc, a tool to weigh the invisible dark matter. We tracked a rebellious cloud of gas orbiting backwards, a captured relic destined to spiral inward and potentially awaken the sleeping giant at the core. We marveled at blue stragglers, old stars masquerading as youth through stellar collisions or cosmic vampirism, and we mapped the invisible magnetic maze that guides the galaxy's gas. We stood in awe of supershell supernova remnants, vast cavities blown by the coordinated deaths of stellar families, and we witnessed a dwarf galaxy in its death throes, being stretched into spaghettification by the Sombrero's tide. We questioned our cosmic rulers, the anomalous Cepheid variable stars whose strange behavior could recalibrate the scale of the entire universe. We delved into the chaotic hearts of globular clusters with frenetic stellar motions, hinting at hidden intermediate mass black holes or the stripped nuclei of ancient galaxies. We uncovered a hidden inferno of star formation, blazing behind the veil of dust in infrared light, and we discovered the potential survival of an ultra-diffuse galaxy, a cosmic ghost that defies tidal destruction. We theorized about an offset active nucleus, a black hole knocked askew by a gravitational wave kick, and we studied the final, beautiful breaths of sun-like stars in the vivid glow of planetary nebulae. We hunted for the shadows of dark matter subhalos within the halo and felt the relentless pressure of the intergalactic wind, stripping the galaxy of its gaseous fuel. We envisioned a tilted inner disk, a separate structure within the core, a fossil of a precise merger, and we considered the potential for a cataclysmic gamma-ray flash from an awakening black hole or colliding neutron stars. We searched for a pristine stream of metal-poor stars, a fossil from the first galaxies, and we listened for the gravitational hum of countless binary systems. We even entertained the existence of a dark galaxy, an invisible companion shaping the Sombrero through pure gravity, and a primordial black hole swarm, ancient relics from the Big Bang that might constitute the dark matter itself. Our journey culminated in the ultimate search, looking for the gamma-ray signature of dark matter annihilation, the possibility that the galaxy's core is a great annihilator where the universe's most mysterious component reveals itself. Each of these 50 strange objects, from the colossal to the nearly invisible, serves as a profound reminder. The Sombrero Galaxy is not a static collection of stars. It is a dynamic, evolving system, a cosmic battlefield where gravity, radiation, and time itself are locked in eternal struggle. Its serene beauty is a masterpiece of illusion, masking a history of violence, cannibalism, and restless energy. Every mystery we've explored, every anomaly that challenges our models, is not a flaw in our understanding but an invitation to look deeper. The Sombrero is a teacher, and its lessons are forcing us to rewrite the story of how galaxies live, interact, and die. The puzzles we see today are the targets for tomorrow's great observatories. The James Webb Space Telescope will peer into the dusty heart with unprecedented clarity, potentially resolving the debate over the twin nucleus. The upcoming Nancy Grace Roman Space Telescope will map the faintest streams of the halo in exquisite detail, tracing the galaxy's assembly history with forensic precision. And future gravitational wave detectors in space may one day tune into the low-frequency hum of the Sombrero's binary black holes, if they exist, listening to the final moments before a cosmic collision. The story of the Sombrero is far from over. In many ways, with these new tools, it is just beginning, and this is where we turn to you. After this tour of 50 cosmic wonders, which one captured your imagination the most? Was it the silent, supermassive black hole, a giant sleeping in plain sight? Or the ghostly tidal streams, the visible graves of long-dead galaxies? Perhaps it was the bizarre blue stragglers, the stellar vampires and collision survivors, or the thrilling possibility that dark matter is annihilating itself in the core. Let us know in the comments below which of these strange objects you found most fascinating. Your curiosity is what drives the exploration forward. The Sombrero Galaxy has kept its secrets for billions of years, but with every new telescope and every new perspective, we pull back another layer, revealing a universe that is stranger, more violent, and more beautiful.